Picture this. An object hurtles toward our sun at 137,000 miles per hour. Scientists predict it will erupt with a massive tail, a cosmic plume visible across millions of miles. But when it emerges from behind our star, there's nothing. Just a brilliant circular light, silent, unbroken, defying every law we know about comets. What you're about to discover could rewrite our understanding of interstellar visitors and perhaps what we consider natural in the cosmos itself. Because this isn't just about a comet behaving strangely. It's about an object that may be choosing its own path. On Halloween 2024, astronomer Chicheng Zhang captured the first post-perihelion images of 3I Atlas. What he saw stunned the scientific community. No tail, no debris cloud, no fragmentation, just a fuzzy sphere of light with an inexplicable central glow. NASA's data confirms the object changed course. Avi Loeb, Harvard astrophysicist, states plainly, "I just don't know what to make of it. How does something lose 10% of its mass near the sun and leave no trace? And why does it look nothing like the hundreds of comets we've watched pass through this same space?" Tonight, we follow the evidence into the unknown. Join me as we trace the journey of 3I Atlas from its discovery in a Chilean desert to its mysterious transformation behind the sun. We'll examine what happened during those invisible weeks, why scientists expected catastrophe, and what the silence means. This is not just astronomy. This is a detective story written in starlight, where every clue leads deeper into the question. What are we really looking at? The Atacama Desert of northern Chile holds some of Earth's clearest skies. Here, the Atlas Telescope Asteroid Terrestrial Impact Last Alert System sweeps the heavens nightly, searching for wanderers against the fixed stars. On July 1, 2025, Atlas found something extraordinary. Artificial intelligence algorithms detected a faint smudge of light moving fast through space. The automated alert went worldwide immediately. This desert carries ancient significance. Long before telescopes, indigenous peoples, the Diaguita the Mole culture watched these same skies, tracked celestial movements, interpreted bright visitors as messengers between worlds. They couldn't have known their descendants would build machines here capable of detecting visitors from beyond our solar system entirely. The object carried temporary designation A11PL3Z. Within days, calculations revealed a remarkable story. Moving at 58 kilometers per second, about 130,000 miles per hour, its trajectory was hyperbolic, not elliptical. This distinction is crucial. Objects bound to our sun travel in ellipses, taking decades or millennia to orbit, but always returning. Hyperbolic trajectories belong to visitors, passing through, moving too fast for the sun's gravity to capture permanently. Only twice before had humanity confirmed such visitors. Oumuamua in 2017, tumbling mysteriously without visible outgassing. 2I Borisov in 2019, behaving like a proper comet with tail and all. Now came 3I Atlas, immediately displaying coma, fuzzy atmosphere of gas and dust when solar radiation heats ice. The designation became official, the third interstellar object discovered by Atlas. Early observations painted familiar patterns. Spectroscopy showed remarkable redness, suggesting dust-rich surfaces and organic molecules processed by billions of years of cosmic radiation. This made sense for an object aged in interstellar space. Hubble captured detailed images July 21st, revealing something unusual, a pronounced plume extending toward the sun. This anti-tail stretched with roughly 10-to-1 elongation in 3 dimensions. Avi Loeb and physicist Eric Quito proposed water ice fragments ejected by sublimating carbon dioxide, strange but explainable through standard physics. By August, the tail was growing. Gemini South showed it stretching 50,000 kilometers. The comet warmed, becoming more active as it approached October 29th perihelion at 136 astronomical units from the Sun. Everything proceeded according to established cometry science, brightening as expected. Tail growing. Trajectory perfectly predictable. Then September brought change. The comet appeared green, suggesting dicarbon molecules or cyanide in the coma. Common in comets as different ices sublimate at different temperatures. By early October, Third Atlas drew close to perihelion, but also moved behind the Sun from Earth's perspective. Ground telescopes went blind. The Sun's glare blocked everything. For nearly a month, Earth-based astronomers could only wait. But space-based observatories, Stereo SOHO GOES 19, designed to monitor the Sun, accidentally witnessed whatever transformation occurred during those crucial weeks behind our star. The stage was set for something unexpected. And when Third Atlas finally emerged from behind the Sun, when Zhang pointed his telescope toward it on that Halloween morning, what he captured would challenge everything scientists thought they understood about interstellar visitors. But I'm getting ahead of myself. Before we discuss what wasn't there, we need to understand what should have been there. We need to understand what every astronomer expected to see, what decades of observation and theory predicted would happen when an icy comet from interstellar space plunged toward our Sun and experienced its fierce embrace for perhaps the first time in billions of years. Picture what should have happened when an icy body passes perihelion at 1.36 AU from the Sun. Surface heated by 770 watts per square meter, 70% of Earth's noontime solar intensity, but continuous unfiltered. Temperatures soaring from -200 Celsius to above freezing. Ices sublimating violently carbon dioxide at -78 degrees water, at 0 methane ammonia, carbon monoxide all turning to gas expanding, pushing outward with tremendous force. This creates the coma, that vast atmosphere extending hundreds of thousands of kilometers. Solar radiation and solar wind push this material away, creating the iconic tail. Not one tail, two. The ion tail of charged particles pointing directly away from the Sun, glowing blue from ionized carbon monoxide. The dust tail of solid particles curving gently behind the comet's path, reflecting sunlight yellow-white. Every comet observed at perihelion develops these tails, every single one. It's as fundamental as leaves growing on trees. Look at Comet Lemon, visible simultaneously with 3I Atlas in late 2024. Gorgeous tail stretching across degrees of sky. Comet Pan-STARRS likewise displayed proper cometry tails. The physics is universal: ice plus solar heat equals outgassing equals tail. Moreover, many comets don't survive perihelion intact. Thermal stress, tidal forces, explosive outgassing these can tear comets apart. Shoemaker-Levy 9 fragmented before hitting Jupiter in 1994. Linear broke apart in 2000. ISON essentially vaporized in 2013. Even survivors emerged changed. Orbits shift from outgassing's rocket effect. Rotation alters. Most obviously, they leave massive debris trails, gas, dust, ice fragments scattering along their orbital path. When Earth crosses these trails, we experience meteor showers. The connection is foundational astronomy. So when 3 Atlas approached perihelion, every astronomer anticipated spectacular outgassing. The carbon dioxide, detected abundantly, would sublimate furiously. Water ice would join the eruption. The comet would brighten dramatically, which it did, and develop a massive, unmistakable tail pushed away from the Sun. October 29th came and went. Perihelion passage occurred on schedule. Space observatories recorded everything through their coronagraphs. Then came October 31st, Halloween. Zhang at Lowell Observatory successfully aimed the 4.3-meter Discovery telescope toward the eastern horizon before dawn, 16 degrees from the Sun, dangerous proximity, requiring careful calculation to avoid equipment damage. Morning twilight already painted the sky, but Zhang captured his image, the first optical ground-based observation of 3I Atlas post-perihelion. What he saw stunned the community. No tail, not small, not faint, no tail at all. A compact circular fuzzy ball of light with concentrated central region. That's it. 2 days later, Zhang repeated observations using a 6-inch amateur telescope. Still no tail. Same circular morphology. Same concentrated central glow. Other observers confirmed it worldwide. Virtual telescope project in Italy. Amateurs everywhere. China's Tianwen-1 Mars orbiter. All showed identical results, a tailless comet. Avi Loeb expressed the collective puzzlement. There should have been a very massive cloud of gas and dust around it based on what we know about comets. We see other comets in the solar system that have beautiful tails away from the sun. Lemon is an excellent example, but in our case of 3I Atlas, it looks like a fuzzy ball of light. He continued. It was heated by 770 watts per square meter. We know that the previous plume was mostly carbon dioxide, which can sublimate at much lower temperature than water ice. So we should have seen it break up or at least disintegrate to a very dense and massive cloud of gas and dust pushed away by solar radiation and wind. But we don't see that. Consider the strangeness. An object rich in carbon dioxide, easily sublimating volatile, passes within 203 million kilometers of the sun and emerges without visible tail. While simultaneously regular solar system comets much farther display magnificent tails visible to backyard telescopes. Loeb suggested ice fragments might vaporize before forming visible tails, exploding off the surface reflecting sunlight initially, then absorbing so much radiation they completely vaporize into gas before traveling far enough to create extended tails. But this raises questions. Why would 3I Atlas behave so differently? The morphology hadn't changed much since July. Hubble images from July 21st showed certain coma structure. Post-perihelion images showed largely the same appearance, as if the comet passed through perihelion's furnace and emerged essentially unchanged. And there was something else emerging from space-based observations. The comet had brightened, much brighter, and faster than mathematical models predicted. But first, let's discuss another anomaly in post-perihelion observations. The color had changed again. Red in July, green in September. Now after perihelion, after experiencing maximum solar heating, blue. Impossibly, inexplicably blue. Color in astronomy is data encoded in wavelengths. When we say a comet appears red, green, or blue, we're describing precise measurements of which wavelengths dominate the spectrum. Red light, 650-700 nanometers. Blue light, 495 nanometers. Different molecules emit characteristic wavelengths when energized by solar radiation. Dicarbon emits green. Sodium emits yellow. By analyzing wavelengths, astronomers determine chemical composition with remarkable precision. But color also depends on reflected sunlight. Dust grains and ice fragments reflect light like any object. Organic compounds coating many comet surfaces after billions of years of radiation tend toward reddish-brown, absorbing blue and green wavelengths preferentially. Dust inherently reddens light, the same phenomenon making sunsets red. A dusty comet should appear reddish. Temperature matters too. Objects emit blackbody radiation depending on temperature. The sun at 5800 Kelvin emits yellow-green. Cooler objects shift toward red. A comet's surface even at perihelion reaches perhaps 272 to 300 Kelvin, far cooler than the sun. Any thermal emission would be infrared, invisible. More importantly, reflected light from such cool surfaces should be redder than sunlight, not bluer. Yet observers detected blue light from 3I Atlas near perihelion, notably blue. Zhang and Battams explicitly noted, color photometry showed 3I Atlas to be distinctly bluer than the sun near perihelion. This shouldn't happen. The sun is our reference, our illumination source. Normal comets reflecting sunlight should match solar color or appear redder from dust and temperature. There's no standard mechanism for appearing bluer. Unless the blue light is emitted rather than reflected, carbon monoxide, when ionized by solar UV, emits bluish light. Other molecules produce blue emission lines. Perhaps 3I Atlas developed unusually strong ion emissions, creating blue appearance. But ion tails are extended structures pointing away from the sun, stretching millions of kilometers. They're not compact glows around nuclei, and observers reported compact circular appearance without obvious extended tail. Could blue light come from concentrated emission near the nucleus, possibly requiring extremely vigorous activity in small areas, which should also produce visible gas streams which weren't observed? Loeb raised another possibility. Always careful to note speculation. A hot engine or a source of artificial light would produce blue emissions. He immediately clarified natural processes could explain it, particularly ionized molecules, but the mention of artificial sources sparked considerable attention. Throughout history, color carried significance. Alchemists documented color changes during experiments: nigredo, albedo, citrinitas, rubedo, representing stages of transformation. Not random but meaningful chemical changes. 3I Atlas's color changes: red, July green, September blue, October echo transformation patterns. Different ices sublimating at different distances create different chemical environments, producing different optical effects. The Maya tracked celestial objects with extraordinary precision, predicted Venus appearances rivaling modern calculations, recorded unusual occurrences. They understood cosmos presented mysteries demanding attention. If Mayan astronomers observed 3I Atlas, they'd certainly mark color changes as significant. Not because primitive, but because unusual phenomena often herald important information, even if cryptic. We're similar today. When 3I Atlas appeared blue when physics predicted red, astronomers marked this significant. Not mystically, but as signal that understanding is incomplete, that this visitor teaches something we don't yet comprehend. The blue coloration persisted briefly when space observatories could observe near perihelion. As 3I Atlas moved away and became visible to ground telescopes, blue faded. By early November, observers reported more neutral whitish appearance, consistent with simple sunlight reflection from dust and ice. Whatever caused the blue was temporarily linked specifically to perihelion passage, an intense solar environment, a phase transition, a brief moment when the comet's chemistry entered unusual states, producing blue light, then returned to typical behavior, moving away from the sun. But that moment happened. The blue light was real, measured by multiple instruments, and it remains unexplained by conventional models. Combined with the missing tail and emerging data about rapid brightening, a pattern forms, not pointing clearly to specific explanations, but a pattern of strangeness, multiple anomalies clustering around one object. And this violation would prove among the most puzzling aspects of the entire 3I Atlas story. When comets approach the sun, they brighten predictably. This relationship follows a power law with exponents typically around -2 to -4. It's nonlinear, but established, quantified by thousands of historical observations. 3I Atlas didn't follow this pattern. Analysis from Stereo Soho and GOES 19 revealed brightening according to a power law with exponent approximately -7.5, roughly twice as steep as even the most active Oort cloud comets at similar solar distances. Zhang and Battens stated clearly, the reason for 3I Atlas's rapid brightening, which far exceeds the brightening rate of most Oort cloud comets at similar radial distances, remains unclear. What does rapid brightening imply? Something released energy or material far exceeding normal cometary behavior. Either composition drastically differed from typical comets, or structure permitted more rapid volatile release, or something else occurred entirely. Comet Hale-Bopp was spectacular because it was large and extremely active, developing massive coma and brilliant tails. Yet even Hale-Bopp's brightening fell within established ranges, extreme but not anomalous. 3I Atlas displayed continuous rapid brightening that accelerated more quickly than models predicted, sustaining this enhanced rate through perihelion approach. The implications are significant. If brightening resulted from outgassing, the standard explanation, then expelled gas and dust volume should have been enormous. That material should scatter sunlight, creating visible clouds' tails, extended structures. But observers didn't see that material. Post-perihelion images showed compact objects, not comets surrounded by massive debris clouds. This creates contradiction. Brightening suggests massive outgassing. Morphology suggests minimal outgassing. Both cannot simultaneously be true unless something unusual is happening. One hypothesis released material was in forms that didn't scatter light efficiently. Gas itself doesn't reflect sunlight well. Only when ionized and fluorescing do we see it glow at specific wavelengths. Dust and ice particles reflect efficiently across many wavelengths, making them visible. If 3I Atlas released primarily gas with minimal dust, it might brighten significantly from fluorescent emission while not developing visible dust tails. But spectroscopy should easily detect fluorescent gas emission lines, and while observations did detect carbon dioxide, water, and other molecules, amounts didn't seem sufficient for extreme brightening. Another hypothesis involves velocity. 3I Atlas moves at 58 kilometers per second, significantly faster than most Oort cloud comets. High velocity means rapidly passing through temperature zones. Ices that normally sublimate gradually might instead hit sublimation temperatures suddenly all at once. But even rapid vaporization should produce visible material. The composition angle is intriguing. JWST observations revealed unusual carbon dioxide enrichment compared to most solar system comets. Carbon dioxide sublimes at much lower temperatures than water ice, around -78 Celsius versus 0 Celsius. Here's an interesting possibility. Carbon dioxide sublimation is endothermic, absorbing heat through evaporative cooling. As carbon dioxide ice turns to gas, it cools surrounding material. If 3I Atlas has large carbon dioxide proportions mixed with water ice, sublimating carbon dioxide might keep water ice frozen longer than expected. Eventually, solar heating overwhelms the cooling effect. When water ice finally begins sublimating, it does so suddenly, in a burst, causing rapid brightening. And perhaps this burst occurs so close to perihelion, when the comet moves at maximum speed through the hottest zone, that sublimated water doesn't have time to create extended tails before dispersing or vaporizing completely. This delayed water ice activation hypothesis potentially explains several observations simultaneously. Carbon dioxide detected months before, perihelion rapid brightening near perihelion, lack of prominent dust tail if timing and dispersion work correctly. Chinese astronomers in 1054 AD observed a guest star appearing suddenly shining bright enough for daytime visibility for weeks, then gradually fading. That guest star was a supernova, the Crab Nebula. They meticulously documented its appearance and evolution. Arab astronomers maintained detailed records of comets, novae, transient celestial phenomena, understanding that heavens occasionally presented surprises demanding careful documentation. The rapid brightening of 3I Atlas may not be as dramatic as supernovae, but within cometry science context, it represents significant anomaly, an outlier pushing established model boundaries. And outliers often teach us most revealing gaps in understanding, hidden assumptions and theories, new possibilities we hadn't considered. But brightening mystery doesn't stand alone. Combined with missing tail, unusual color, and evidence that the comet changed course, a pattern emerges, not of single anomaly but of cluster. A pattern of strange behaviors together, suggesting something genuinely unusual about this interstellar visitor. Gravity is deterministic, mathematical, predictable. Give me position, velocity, and mass, and I can predict future movements with precision, except when non-gravitational forces intervene. For comets, these forces arise from outgassing's rocket effect. Gas jets erupting asymmetrically push comets in specific directions. These accelerations are small, typically fractions of a % of solar gravitational pull, but measurable and well documented. David Farnokia at NASA's Jet Propulsion Laboratory analyzed 3I Atlas's trajectory using all available positional data from July through October. His analysis detected non-gravitational acceleration with both radial and tangential components. This isn't surprising for comets. What draws attention is context. 3I Atlas showed non-gravitational acceleration, but lacked obvious visible outgassing that should accompany it. Oumuamua experienced this same situation. Precise tracking revealed small but definite non-gravitational acceleration, yet showed no visible coma or tail. This sparked considerable debate. Some proposed outgassing producing no visible dust, perhaps pure hydrogen gas that wouldn't reflect light. Others, notably, Avi Loeb suggested if outgassing didn't explain acceleration, perhaps other mechanisms should be considered.
Now 3I Atlas presents similar gaps. The object changed course. NASA confirmed it. The change is small but measurable and statistically significant. Yet mechanism remains unclear. To change trajectory measurably, non-gravitational force must impart sufficient momentum. Calculations depend on the comet's mass, force, magnitude, and duration. Unfortunately, we don't know 3I Atlas's mass precisely because size estimates range from 440 meters to several kilometers, spanning more than an order of magnitude. If the nucleus is small, modest outgassing could produce measurable acceleration. If large, much more vigorous outgassing would be required. Observations suggest the nucleus is probably 1 to 2 kilometers diameter. At that size, producing measured non-gravitational acceleration would require expelling considerable gas, probably tons per second at peak activity. That gas has to go somewhere, expanding into space, creating coma and tail. Or so it should.
Perhaps gas jets are highly collimated, focused in specific directions, rather than radiating broadly. This could create thrust without producing large diffuse comas. But collimated jets should be visible as localized bright spots, and high-resolution Hubble images didn't show clear evidence. Or perhaps outgassing occurs in regions facing away from our line of sight. Geometrically possible but statistically unlikely, especially given observations from multiple angles. The comet's composition includes only 4 to 5% water, unusually low but not unprecedented. If most nucleus consists of more volatile ices like carbon dioxide, these could outgas vigorously without producing as much visible dust. Water ice tends to carry dust particles when sublimating. More volatile ices sublimate more cleanly, producing primarily gas. But spectroscopy should detect that gas through emission lines. While carbon dioxide has been clearly detected, amounts inferred don't seem sufficient for both rapid brightening and non-gravitational acceleration. Ancient navigators, particularly Polynesian voyagers, colonizing Pacific islands, developed extraordinary celestial navigation skills. They tracked stars rising and setting at specific horizon points, noted planetary paths against stellar backgrounds, understood celestial bodies follow predictable patterns. When something deviated from predicted paths, they noticed. Babylonian astronomers kept meticulous records on clay tablets, tracking planetary movements, wanderers, against fixed stars. Over centuries, they accumulated enough data to predict positions and eclipses with impressive accuracy. But occasionally they recorded anomalies, unusual positions, unexpected behaviors that didn't fit patterns. The concept of celestial bodies having agency pervades ancient mythology. Greek myths spoke of wandering star gods. Egyptian cosmology depicted sun god Ra sailing his bark across sky each day, journey of will and purpose rather than mechanical orbit. We understand now these aren't gods making choices, but objects following physical laws. Yet when objects like 3I Atlas change course in ways we can't fully explain, there's an echo of ancient wonder. Not because we believe in divine intervention, but because we're confronting something current models don't adequately describe. The parallels with Oumuamua add weight to the puzzle. One interstellar object showing non-gravitational acceleration without obvious outgassing might be strange one-off. 2 begins suggesting pattern. Perhaps interstellar objects because of different formation environments or billions of years. Traveling through radiation-intense interstellar medium behave differently than solar system comets in ways we don't yet understand. The trajectory change means something physical occurred. Energy was transferred, momentum was imparted. That's certain. What remains uncertain is mechanism. And in science, unexplained mechanisms are invitations to investigate further, gather more data, refine theories. As 3I Atlas continues, its outbound journey, precise tracking of its position will help refine our understanding of these non-gravitational effects. If the acceleration continues in a predictable way, correlated with solar distance, it strongly supports an outgassing explanation, even if we can't see the gas directly. If it behaves erratically or ceases suddenly, that would suggest something else, something more complex about the comet's activity or structure. The December approach, when the comet reaches its closest point to Earth, offers the best opportunity for these precise measurements. Multiple observatories worldwide will be tracking its exact position against background stars, creating an astrometric dataset of unprecedented accuracy for an interstellar visitor. Every observation adds a data point. Every data point constrains the possibilities. And eventually, through the accumulation of evidence, the explanation will emerge. That's how science works, not through sudden revelations, but through patient systematic gathering of information until the picture clarifies. But before we reach December, before those crucial observations that may help resolve some of these mysteries, we need to acknowledge perhaps the most frustrating aspect of the 3I Atlas story, the data that wasn't released, the images that remain hidden, and the questions about transparency in science that this situation has raised. October 2025 brought an alignment both astronomical and unfortunate. As 3I Atlas passed through perihelion on October 29th, it was positioned on the opposite side of the Sun from Earth's perspective. Ground-based telescopes couldn't observe it. The Sun's overwhelming brightness and the geometric impossibility of looking through one. 4 million kilometers of solar plasma made observation from Earth's surface impossible. This is not unusual. Comets regularly pass through solar conjunction the moment when they're aligned with the Sun from Earth's viewpoint, and we simply wait until they emerge on the other side. It's frustrating for astronomers, certainly, because perihelion is when comets are typically most active, most spectacular, most scientifically interesting. But it's a predictable consequence of orbital geometry. What made October 2025 different was the political context. On October 1st, the United States federal government entered a shutdown due to budget disputes in Congress. Non-essential government services ceased. Federal employees were furloughed. And NASA as a government agency was significantly affected. NASA's Mars Reconnaissance Orbiter, which has been studying Mars since 2006, carries an instrument called HiRISE High-Resolution Imaging Science Experiment. HiRISE is a remarkable camera capable of resolving features on Mars's surface as small as a meter across from orbital altitude. It's primarily designed for mapping Martian terrain, studying geological features, and scouting potential landing sites for future missions. But in early October 2025, 3I Atlas passed within approximately 30 million kilometers of Mars. That's close enough and the relative geometry favorable enough that HiRISE could potentially observe the comet. Not with meter-level resolution, obviously the comet was 30 million kilometers away, not in orbit but with a spatial resolution of about 30 kilometers per pixel. 30 kilometers per pixel might not sound impressive, but context matters. The best Hubble Space Telescope images of 3I Atlas taken in July, when the comet was 277 million kilometers from Earth, achieved a resolution of roughly 90 kilometers per pixel. The high-rise observations from Mars occurring when the comet was much closer and from a different viewing angle would achieve 3 times better resolution. Moreover, the viewing geometry from Mars was sideways relative to the Sun. Imagine looking at a comet from Earth, we see it with the Sun behind us, or at some angle, but we're looking at the illuminated side, the side facing sunward. From Mars's perspective in early October, looking at 3I Atlas would provide a profile view seeing the structure of any gas or dust emissions from the side rather than head-on. This perspective is invaluable for understanding three-dimensional structure. The high-rise team planned these observations. They pointed the camera. They captured images on October 2nd and 3rd during the crucial period when the comet was passing through perihelion, when it was experiencing maximum solar heating and should have been most active. Then, silence. As of early November 2025, those images had not been publicly released, not posted to NASA's websites, not published in scientific journals, not shared with the broader scientific community. Just silence. Avi Loeb, who had been following 3I Atlas closely and communicating with various researchers about ongoing observations, became increasingly vocal about this lack of data release. He appeared on Joe Rogan's podcast on October 30th, discussing 3I Atlas and raising the issue of the unreleased high-rise images. When Rogan asked whether the delay might indicate the images showed something unusual, something NASA wanted to hide or carefully evaluate before release, Loeb dismissed that speculation with characteristic bluntness. The delay is probably not a sign of extraterrestrial intelligence, but rather of terrestrial stupidity. He attributed the problem to the government shutdown, arguing that science was being held hostage to political dysfunction. Routine operations, including data processing and public release, were disrupted because personnel were furloughed and systems weren't running normally. "We should not hold science hostage to the shutdown politics of the day," Loeb stated. The scientific community would have greatly benefited from the dissemination of this time-sensitive data as astronomers plan follow-up observations in the coming months. The frustration is understandable. Astronomy, unlike laboratory science, can't repeat experiments. When an interstellar object passes through the inner solar system, that's a unique event, never to be repeated. Every observation is precious. Every data point matters. And timing is crucial. Observations from different perspectives and different distances must be coordinated to build a comprehensive picture. If the high-rise data could inform what to look for in subsequent Earth-based observations, its value multiplies. But delayed by weeks or months, its utility diminishes. Scientists are planning observation strategies now, writing telescope proposals, scheduling instruments. They need information in real time to make informed decisions. This wasn't a theoretical concern. Loeb, following the podcast appearance, reached out to Congresswoman Anna Paulina Luna, a Republican representative from Florida who has taken interest in unexplained aerial phenomena and scientific transparency issues. Representative Luna responded swiftly. On October 31st, Halloween, the same day John captured his first post-perihelion images from Lowell Observatory, Luna sent a formal letter to acting NASA Administrator Shaw Duffy. The letter was direct and specific. Luna requested the immediate release of the high-rise images, noting their superior resolution compared to Hubble observations. She emphasized the scientific importance of this data. This information is of great importance to advancing our understanding of interstellar visitors and their interaction with our solar system. But Luna's letter went further. She also requested any supplementary data from Mars missions that may have detected unusual activity near Mars during 3I Atlas's closest approach. The phrasing "unusual activity" raised eyebrows. What kind of unusual activity? The letter didn't specify, leaving interpretation open. Additionally, Luna encouraged NASA to fund additional observations, using the Juno spacecraft currently orbiting Jupiter, suggesting all available instruments, including radio sensors, be employed when 3I Atlas passes near Jupiter in March 2026. 3 days later, on November 3rd, Luna followed up publicly on X, tagging Administrator Duffy directly, "Can you please see letter below? We would like to see images of 3I Atlas." She attached the full text of her October 31st letter. The pressure was now public visible and coming from an elected official with oversight capacity. Congress controls NASA's budget and can hold hearings on agency operations. A congressional request for data carries weight. NASA's response was measured. Administrator Duffy, in her reply to a question from Kim Kardashian on X about 3I Atlas, yes. Kim Kardashian had tweeted asking, "What's the T on 3I Atlas?" when stated that the comet was the third known interstellar comet, exhibiting no signs of being anything other than a natural object and posing no threat to Earth. NASA's lead scientist Tom Statler elaborated to media outlets that 3I Atlas very strongly resembles known comets, and that speculation about artificial origins was unfounded. These statements addressed the public's curiosity and tamped down sensationalistic speculation, but they didn't address the core issue: why hadn't the high-rise data been released? Loeb responded to Statler's comments in interviews, arguing that declaring the matter settled without releasing all available data was counterproductive because the public deserves to hear different scientific perspectives. He maintained that transparency, not reassurance, should be the priority. Investigation by journalist Christina Gomez revealed that Luna had actually sent 2 letters to NASA regarding 3I Atlas. The first, dated July 31st, proposed redirecting Juno to intercept the comet. That letter cited Loeb's analysis suggesting a specific thrust maneuver on September 14th could position Juno for close observations during 3I Atlas's March 2026 Jupiter flyby. The estimated cost, $15 million for a 6-month mission extension. That first letter received no response. The second letter, in late October, after perihelion shifted strategy, demanding release of data already collected rather than proposing new observations. The situation crystallizes a genuine tension in modern science. On one hand, researchers need time to process data, to validate it, to understand it before public release. Premature release of unvalidated data can lead to misinterpretations, false claims, and confusion. Scientists are cautious, and rightly so. On the other hand, in an age of instant communication and public interest in science, delays can breed suspicion. The longer data remains unreleased, the more speculation fills the void. And for time-sensitive observations like an interstellar object passing through our solar system, delays have practical consequences for follow-up observation planning. There's also a historical context worth acknowledging. The Library of Alexandria. That great repository of ancient knowledge represented humanity's accumulated understanding of the world. Its destruction, whether by fire, neglect, or deliberate action, remains debated, symbolizes the fragility of knowledge, how easily it can be lost or hoarded. Ancient Sumerian astronomical records were kept by priestly classes, not shared broadly. Knowledge was power, literally. The ability to predict eclipses, to mark the seasons, to interpret omens, gave priests considerable social authority. Information was controlled, parceled out, used politically. The modern scientific ethos stands in contrast. Open publication, peer-review data, sharing these principles emerged from recognizing that knowledge advances fastest when widely disseminated and collectively evaluated. Yet even today, data access can be restricted by institutional policies, funding agencies, national security concerns, or simply administrative dysfunction. The high-rise situation likely stems from bureaucracy rather than conspiracy. Processing planetary science data requires specialized personnel and systems. During a government shutdown, those resources may not have been available. The images probably exist in raw form but haven't been processed into scientifically useful products ready for public release. But the perception problem remains. When people expect transparency and encounter delay, especially regarding an object of intense public interest, suspicion fills the gap. Some will wonder if the images show something controversial, something that requires careful framing before release. Others will assume simple incompetence or bureaucratic inertia. Neither interpretation flatters the institution. As of this writing, the high-rise images remain unreleased. NASA has not provided a specific timeline for their publication. The scientific community continues waiting. And 3I Atlas continues moving through space, gradually receding from Mars, approaching closer to Earth for December's observations. Perhaps when those images do emerge, they'll show nothing unexpected, a fuzzy comet consistent with other observations interesting but not revolutionary. Or perhaps they'll reveal structural details, activity patterns, or features that help resolve some of the anomalies we've been discussing. Either way, the episode highlights a question that extends beyond this particular comet who owns cosmic discoveries. When publicly funded instruments observe interstellar visitors or other astronomical phenomena, how quickly should that data become public? What balance should exist between thorough scientific analysis and timely data release? These aren't easy questions. They intersect science, politics, public trust, and practical logistics, but they're important questions worth considering seriously. Because the universe doesn't wait for bureaucratic processes. 3I Atlas passed perihelion on schedule, indifferent to government shutdowns or data release policies. It's continuing its journey, whether we observe it thoroughly or not. The only question is how much we'll learn before it's gone forever. And that brings us back to something fundamental: the human impulse to watch, to record, to understand. That impulse has driven astronomy since ancient times. It's what motivated Babylonian scribes to track planetary positions night after night. It's what drove Mayan astronomers to build elaborate observatories and develop sophisticated predictive models. It's what compels amateur astronomers today to wake before dawn in cold November darkness, pointing their backyard telescopes toward a faint smudge of light from another star system. That impulse doesn't belong to NASA or any institution. It belongs to all of us, to anyone who looks up and wonders. And when something remarkable passes through our cosmic neighborhood, when an interstellar visitor older than Earth itself sweeps past the sun, that's humanity's moment, not just any single nation's or agency's. The images will eventually be released. The data will become available. Science will continue. But the episode serves as a reminder that the process matters, that transparency builds trust, and that the cosmos, in its patient enormity, rewards those who observe carefully and share generously. Now let's turn from what we haven't seen to what humans have seen for millennia: visitors in the sky, unexplained lights, celestial wanderers. And let's ask whether our ancestors, with their different frameworks and vocabularies, might have witnessed similar interstellar passages without recognizing them as such. The night sky has been humanity's first book, the original text from which we learned about cycles, patterns, cause and effect. Long before written language, before agriculture, before permanent settlements, humans watched the heavens. We tracked the moon's phases, learned that certain stars rose at certain seasons, noticed the wandering lights that moved against the fixed stellar background, and occasionally, rarely, something unexpected appeared. A bright star where none had been before, a fuzzy smudge with a tail stretching across the sky, a light that didn't fit the established patterns. The Babylonians, whose civilization flourished in Mesopotamia from roughly 1900 BCE to 539 BCE, were perhaps history's most meticulous astronomical record keepers. They created systematic observational programs, tracking celestial phenomena night after night, generation after generation. Their observations were inscribed on clay tablets using cuneiform script. These weren't casual observations. They were rigorous quantitative records noting positions, timings, and characteristics of planets, the moon eclipses, and unusual phenomena. The Babylonians developed mathematical models to predict planetary positions and eclipse timings. Their accuracy was impressive. Modern scholars analyzing these tablets can identify specific astronomical events and verify the Babylonians' calculations. Among their records are numerous mentions of comets. They called them various names depending on appearance: the long-tailed star, the bearded star, the horned star. They noted when comets appeared how long they remained visible, their brightness, the direction of their tails. They tracked them as carefully as they tracked planets. But here's a question: would the Babylonians have recognized an interstellar comet as distinct from a solar system comet? Almost certainly not. They had no concept of interstellar space, no framework for understanding that some comets might originate beyond the sun's gravitational domain. A comet was a comet regardless of its origin. So if an object like 3I Atlas passed through the inner solar system in, say, 1200 BCE, Babylonian astronomers would have recorded it, but simply as another comet, not noting anything that would signal to us today that it was interstellar. The Chinese maintained astronomical records even longer than the Babylonians. Chinese astronomical observations extend back more than 3,000 years, with systematic records dating to at least the Shang dynasty, 1600–1046 BCE. These records were kept by court astronomers whose job was to track celestial events and interpret them for the emperor. The Chinese were particularly interested in transient phenomena, novae, supernovae comets. They called comets broom stars or guest stars, depending on appearance. They documented dozens, perhaps hundreds of cometary apparitions over the centuries. Their records are so detailed that modern astronomers have used them to trace the historical appearances of periodic comets, like Halley's, confirming its roughly 76-year orbit extends back millennia. In 1054 CE, Chinese astronomers recorded a guest star in the constellation Taurus that appeared suddenly, shone brilliantly enough to be visible during daytime for weeks, then gradually faded over months. That observation, along with corresponding records from Arab astronomers, documents the supernova explosion that created what we now call the Crab Nebula. Their careful observations help modern astrophysicists understand the timeline and energetics of that stellar death. But among those countless comet records, how many might have been interstellar visitors? Statistical analysis suggests that interstellar objects may be relatively common, with estimates indicating perhaps one passing through the inner solar system at any given time, though most too faint or inactive to detect. If this rate holds throughout history, then over 3,000 years of Chinese observations, dozens or even hundreds of interstellar comets might have passed through, recorded as ordinary comets because the observers had no way to distinguish them. Perhaps some of those ancient records describe comets with unusual characteristics, anomalous behaviors, unexpected brightness, changes, peculiar appearances that might, if we could analyze them with modern tools, reveal interstellar origin. The Maya of Mesoamerica were master astronomers despite having none of the instruments we associate with astronomy. No telescopes, no astrolabes, no precision measuring tools. Yet they tracked Venus with extraordinary accuracy, predicting its appearances and disappearances as morning and evening star using complex mathematical tables recorded in their codices. The Dresden Codex, one of the few surviving Mayan manuscripts, contains astronomical tables covering Venus cycles, eclipse predictions, and various other celestial phenomena. The precision is remarkable. Their Venus tables align with modern calculations to within hours over centuries. The Maya built observatory structures aligned to specific celestial events. El Caracol at Chichen Itza, with its circular tower and viewing slots, aligns with Venus's extreme positions on the horizon. Other structures mark solstices, equinoxes, and stellar risings. This wasn't idle curiosity. Mayan cosmology intertwined celestial and terrestrial realms. The movements of planets, the phases of the moon, the appearance of unusual celestial visitors, all carried meaning within their worldview. They incorporated these observations into their calendrical systems, their religious practices, their understanding of time itself. When comets appeared, the Maya surely recorded them, though many of these records were destroyed by Spanish conquistadors and missionaries who viewed Mayan texts as pagan heresy. What survives hints at a sophisticated observational tradition that likely documented comets, along with planets and stars. But again, they would have had no framework to distinguish interstellar from solar system comets. An unusual visitor was unusual, certainly worth recording, worth interpreting, but the specific distinction we make today about gravitational binding to the sun versus hyperbolic trajectories wouldn't have been meaningful to them. Let's consider a specific historical example, the Star of Bethlehem. The Gospel of Matthew describes a bright star that appeared around the time of Jesus' birth, guiding wise men from the east to Bethlehem.
Countless theories have been proposed for what this star might have been astronomically. A conjunction of planets, particularly Jupiter and Saturn, occurred in 7 BCE, creating a close approach that might have appeared as an unusually bright star to observers. A supernova or nova could have created a new bright star, though records from other civilizations don't clearly document such an event around that time. A comet is another possibility. Bright comets have often been interpreted as omens or signs in various cultures. Or could it have been an interstellar visitor? An object passing through the inner solar system, brightening rapidly, perhaps behaving anomalously enough to draw particular attention from observers who tracked such things carefully. We can't know. The astronomical records from that period aren't detailed enough to reconstruct specific events with certainty.
The Star of Bethlehem might be theological rather than astronomical, a narrative device rather than literal celestial phenomenon. But the question illustrates something important. Throughout history, humans have noticed unusual things in the sky and incorporated them into cultural narratives. Some of those unusual things might have been genuinely unusual in the sense we mean today, objects from beyond our solar system. Visitors carrying chemistry and structures formed around other stars. Egyptian astronomy focused heavily on stellar risings and settings, particularly the heliacal rising of Sirius, which coincided with the Nile's annual flooding and marked their new year. Their cosmology envisioned the sky as a goddess nut whose body arched over the earth with stars either painted on her body or decorations hanging from her. This isn't primitive astronomy. It's a different framework, a different vocabulary for describing the same phenomena we observe today. When we say a star rises, we're using metaphorical language too. The star isn't actually rising. Earth's rotation makes it appear to rise. Different metaphor, same observed fact. The Egyptians tracked planets, calling them the stars that know no rest, because they moved against the fixed stellar background. They incorporated celestial observations into their religious architecture temples, aligned to solstices, pyramids, aligned to stellar configurations. They understood celestial mechanics at a practical level, even if their theoretical framework differed from ours. Stonehenge, built beginning around 3000 BCE in what's now England, embodies astronomical knowledge in stone. The monument's alignment to solstice sunrises and sunsets is well documented. Some researchers argue it also functioned as a lunar observatory tracking the moon's complex cycles. The precision of these alignments required careful multi-generational observation and remarkable dedication to preserving and transmitting knowledge. These ancient peoples weren't waiting for someone to explain the universe to them. They were actively observing, recording, interpreting. They built models, different models than ours, expressed in different languages and frameworks, but models nonetheless that made predictions and guided behavior. When something unusual appeared in their skies, they noticed. They recorded it within their systems. They interpreted it according to their frameworks. And while we can't retrospectively identify which of those ancient observations might have been interstellar visitors, we can appreciate that our current curiosity about 3I Atlas connects directly to that ancient impulse. Humans have always wondered about visitors from beyond. The difference today is that we have the tools to recognize them for what they are, and the physics to understand where beyond means. But the fundamental response, that mixture of awe, curiosity, and the drive to understand, is as old as our species. The continuity is profound. A Babylonian astronomer 3,000 years ago, watching a bright comet arc across the pre-dawn sky, felt something similar to what amateur astronomers feel today when they capture 3I Atlas through their backyard telescopes. The questions differ in sophistication, the explanations differ in framework, but the underlying experience, the confrontation with cosmic mystery, the recognition that we're witnessing something rare and significant transcends time and culture, and perhaps there's wisdom in that ancient approach worth remembering. The Babylonians didn't need to understand the universal law of gravitation to track planetary motions accurately. The Maya didn't need Newton's equations to predict Venus's positions. They observed carefully recorded, meticulously built models that worked within their purposes and remained humble before the enormity of what they were studying. Modern science adds extraordinary power to that ancient foundation. We can determine chemical compositions from spectroscopy. We can calculate trajectories with computer precision. We can detect objects billions of light years away, but we still at base do what those ancient astronomers did. We look up, we notice patterns, we record anomalies, and we wonder. 3I Atlas is anomalous. We've established that through multiple lines of evidence. But it's anomalous within our framework relative to our models. It's behaving in ways our current cometry science doesn't fully predict. Future observations and refined theories may resolve these anomalies, incorporating them into an expanded understanding that makes them normal rather than exceptional. Or the anomalies might persist, might represent genuine discoveries about how interstellar objects differ from solar system comets, how matter behaves after billions of years in the radiation-intense environment between stars, how chemistry and physics play out under conditions we've never previously encountered. Either way, we're witnessing something remarkable, an object from another star system passing through our neighborhood, offering us a chance to study matter formed in a different time and place. Every photon we collect, every spectrum we analyze, every trajectory calculation we refine adds to our understanding. And centuries from now, if humanity maintains its astronomical traditions, future observers will look back at our records of 3I Atlas much as we look back at ancient records of comets and supernovae. They'll see what we got right and what we misunderstood. They'll have better tools, refined theories, more context. But they'll recognize in our observations the same fundamental drive that motivated the Babylonians, the Maya, the Chinese court astronomers, the builders of Stonehenge. The universe speaks. We listen. Sometimes what it tells us challenges our understanding, and those moments, uncomfortable, puzzling, thrilling, are when we learn most. Now let's shift focus from professional observatories and ancient astronomers to the modern amateur observers who are currently capturing 3I Atlas with equipment many people own, participating directly in this cosmic moment. Because one of the most remarkable aspects of this story is its accessibility, how an interstellar visitor has become visible, not just to institutions, but to individuals, democratizing discovery in real time. There's something profoundly democratic about the night sky. It doesn't check credentials before revealing its wonders. A photon that traveled from 3I Atlas across millions of kilometers doesn't care whether it lands on the mirror of the Hubble Space Telescope or the lens of a 6-inch reflector in someone's backyard. The information encoded in that photon, its wavelength, its intensity, the story it tells about where it came from remains identical regardless of which instrument captures it. This accessibility has defined amateur astronomy. Since Galileo first pointed a telescope skyward in 1609, Throughout history, significant astronomical discoveries have come from amateur observers. Caroline Herschel discovered 8 comets in the late 1700s. William Herschel, her brother, discovered Uranus, a planet, using a telescope he built himself. These weren't professionals with institutional backing. They were passionate individuals with optical instruments and dedication. The tradition continues. In August 2019, Gennady Borisov, an amateur astronomer in Crimea using a telescope he'd personally built, discovered the second confirmed interstellar object, later designated 2I Borisov. His discovery, made with equipment modest by professional standards, provided humanity with crucial data about interstellar visitors. Professional observatories around the world subsequently observed Borisov extensively, but the initial detection came from an amateur's dedication. Now 3I Atlas offers something unprecedented, an interstellar object bright enough and well-placed enough that experienced amateur astronomers can observe it directly. Not just photograph it, but track it, study it, contribute meaningfully to the scientific understanding of this visitor. When Qicheng Zhang successfully captured 3I Atlas on November 2nd using a 6-inch telescope, a 152mm Ritchie-Chrétien reflector, he demonstrated that the comet was accessible to serious amateur equipment. Within 48 hours, confirmation images began appearing online. Observers across the United States, then Europe, then globally, started sharing their captures. An observer in Arizona using a Celestron 8-inch Schmidt-Cassegrain telescope reported capturing the comet clearly in a stack of 20 30-second exposures. Someone in New Mexico with a 10-inch Dobsonian reflector posted a sketch made at the eyepiece showing the comet as a diffuse circular glow with a faint extension toward the southwest. A photographer in California stacked 200 frames, taken with a telephoto lens mounted on a tracking mount, producing an image that showed not just 3I Atlas but several background galaxies in the same field of view, ancient light from billions of light years away, sharing the frame with the interstellar visitor. The community aspect of amateur observation has been remarkable. Online forums, social media groups dedicated to astrophotography, and specific pages tracking 3I Atlas have become centers of information exchange. Observers post their images with acquisition details, what telescope they used, what exposure settings, how they processed the data. Others offer tips how to deal with light pollution, how to manage dew formation on optics during cold pre-dawn sessions, what processing techniques work best for enhancing faint details. There's no competition here, no sense of racing to get the best image. Instead, there's collaboration. Someone who successfully captured the comet shares exact settings, helping others who've struggled with clouds or equipment issues. Knowledge flows freely. This is citizen science in its purest form, people contributing not for career advancement or publication credits, but simply because they're curious, because they want to see an interstellar visitor with their own eyes or cameras, because they want to participate in this cosmic moment. The technical requirements for observing 3I Atlas are modest by modern astrophotography standards. The comet is currently around magnitude 9 to 10, which places it well beyond naked eye visibility. The faintest stars visible to unaided human eyes under perfect conditions are around magnitude 6, and each magnitude step represents a brightness difference of about 2.5 times. So magnitude 9 is roughly 16 times fainter than what we can see without help. But magnitude 9 is easily within reach of binoculars under dark skies, though it appears very faint and requires knowing exactly where to look. A 4-inch telescope makes it readily visible as a fuzzy patch distinct from background stars. 6 to 8-inch telescopes, the workhorses of amateur astronomy, the size many serious hobbyists own, show the comet clearly with obvious coma structure visible. Larger amateur instruments, 10 inches and up, can begin to reveal details, subtle variations in the coma, hints of structure that professional observations have documented. The imaging process requires patience, but not exotic equipment. A tracking mount is essential. This is a motorized device that rotates the telescope to compensate for Earth's rotation, keeping celestial objects centered in the field of view during long exposures. Without tracking, stars appear as trails across the image within seconds, making deep sky photography impossible. A camera, either a dedicated astronomy camera, a CCD, or CMOS sensor optimized for low-light imaging, or a modified digital single-lens reflex camera, DSLR, captures individual frames. Most observers use exposures between 30 seconds and 2 minutes, balancing the need to gather light against the comet's motion across the sky relative to background stars. Then comes stacking, combining dozens or hundreds of individual frames, using software like Deep Sky Stacker or PixInsight. This processing averages out random noise while preserving real signal, transforming a collection of noisy, grainy individual images into a clean final result. But 3i Atlas presents a unique challenge compared to imaging stationary deep sky objects like galaxies or nebulae. The comet is moving relatively quickly against the stellar background. Typical stacking software tracks stars, aligning each frame so stars overlap perfectly. But if you do this with comet images, the comet itself becomes a streak because it's moving while the stars are fixed. The solutions stack on the comet instead of the stars. Some programs have built-in comet stacking modes. Others require manual alignment using the comet as the reference point. The result is that stars appear as streaks or trails, while the comet remains sharp, the opposite of normal astrophotography, but correct for tracking a moving object. Several amateur observers have turned this challenge into art. Images showing 3i Atlas as a crisp, detailed point with radiating star trails around it create a visual representation of the comet's motion through our solar system. One photographer created a time-lapse animation from frames taken over 3 hours showing the comet's movement against the stellar background in real time. These aren't just pretty pictures, they're demonstrations of orbital mechanics made visible. For many amateur astronomers, 3i Atlas represents their first opportunity to observe an interstellar object. Oumuamua in 2017 was far too faint for amateur equipment. By the time its interstellar nature was confirmed, it had already passed through the inner solar system and was receding, visible only to large professional telescopes. 2i Borisov in 2019 was more accommodating, reaching about magnitude 15 at its brightest, which made it accessible to experienced amateurs with larger telescopes and imaging equipment. But magnitude 15 requires dedication, decent-sized instruments, and good observing sites. 3i Atlas, at magnitude 9 to 10, is significantly brighter than Borisov ever was. This brightness difference, about 5 magnitudes, represents a factor of 100 in brightness. That's the difference between an object requiring a 12-inch telescope and an object visible in a 4-inch telescope. That's the difference between something only dedicated deep sky imagers can capture and something accessible to anyone with modest equipment and enthusiasm. This accessibility has educational implications. High school astronomy clubs are organizing pre-dawn observing sessions, allowing students to see an actual visitor from another star system through their school's telescope. That's not a classroom abstraction, that's photons from another stellar neighborhood entering their eyes. The impact can be profound. Universities are incorporating 3i Atlas observations into undergraduate astronomy labs. Students learn about orbital mechanics, not from textbook diagrams, but by tracking a real object moving across the sky. They learn about spectroscopy by analyzing the comet's spectrum. They learn about the scientific method by formulating hypotheses about the comet's behavior and testing them against observations. The comet becomes a teaching tool, making abstract concepts concrete. Planetariums and science centers have hosted public viewing events, though the pre-dawn timing makes scheduling challenging. Still, the effort is worthwhile. allowing the general public to observe an interstellar visitor even if it appears as just a fuzzy patch of light connects people viscerally to concepts that might otherwise remain abstract. The observing conditions have been progressively improving through November and into December for Northern Hemisphere observers. The comet's altitude above the horizon increases each morning as its orbital motion carries it northward from our perspective. Higher altitude means darker backgrounds, less atmospheric glow from the approaching sunrise, and more observation time before twilight brightens the sky. By mid-November 3rd, Atlas rose about 2 hours before the sun at mid-northern latitudes, giving observers a comfortable window. Early December brings even better conditions, with the comet rising 3 or more hours before sunrise high enough in the sky that atmospheric extinction, the dimming effect of looking through more air near the horizon, is minimal. The cold November and December mornings bring challenges: numb fingers, fogging optics equipment that doesn't like cold temperatures, but also advantages. Winter air tends to be clearer than summer air, less haze and humidity. For astronomers, cold and clear beats warm and muggy. You wear layers, you bring thermoses of hot coffee or tea, you embrace the discomfort because the seeing conditions make it worthwhile. Southern Hemisphere observers face different conditions. The comet's current trajectory and position favor northern viewers, though it remains visible from southern latitudes with effort. Observers in Australia and South America report needing clear horizons and careful timing to catch the comet low in the sky before sunrise. This geographic bias in visibility has concentrated observations in North America, Europe, and Asia, though dedicated Southern Hemisphere astronomers still contribute data. Equipment discussions have taken on new relevance.
Which eyepieces provide the best views of low-surface brightness objects like comet comas? What camera sensors are most sensitive to the wavelengths where cometary emissions occur? How do different telescope designs, refractors versus reflectors, Newtonian versus Schmidt-Cassegrain, affect contrast when observing against twilight skies? These technical questions, usually abstract, now have a concrete application. The answers matter because observers want to see 3i Atlas as clearly as possible. Some advanced amateurs have gone beyond simple imaging to attempt more sophisticated observations. Spectroscopy, once exclusive to professional astronomy, has become accessible to dedicated amateurs with specialized equipment. A handful of observers have obtained low-resolution spectra of 3i Atlas identifying emission lines from carbon compounds in the coma.
These amateur spectra won't replace professional observations from instruments like the James Webb Space Telescope, but they demonstrate what's possible with commitment and modest equipment. And the data gets shared online, added to the collective understanding of the comet's composition. Photometry precise brightness measurements is another area where amateurs contribute. By carefully measuring the comet's magnitude over multiple nights using calibrated techniques, observers can track brightness changes that might indicate rotational variations in the nucleus or changes in outgassing activity. Professional photometry is more precise, certainly, but amateur observations provide temporal coverage that would be impossible otherwise.
A network of amateur photometrists can monitor 3i Atlas every clear night from locations around the world, creating a continuous light curve that captures short-term variability professional observatories might miss due to weather or telescope scheduling constraints. The experience of observing 3i Atlas has been described by many amateurs as humbling and awe-inspiring. One observer posted about setting up their telescope at 4:30 in the morning, hands numb from cold, watching their breath form clouds in the beam of their red headlamp. When the comet finally appeared in the eyepiece, just as predicted by the ephemeris, the table of predicted positions, they reported feeling a connection across billions of years and incomprehensible distances. That fuzzy patch of light was matter from another star system older than Earth that had traveled through the void to appear in their telescope on this particular morning.
Another observer described the challenge of explaining to neighbors why anyone would be outside in freezing temperatures before dawn, pointing a tube at the sky. After showing them the comet through the eyepiece and explaining what they were seeing, the neighbor stood silently for a moment before saying simply, "We're really not alone, are we?" That sense of perspective of understanding Earth as one small world in a galaxy filled with planetary systems comes through powerfully when viewing an interstellar visitor. This isn't abstract knowledge from a textbook. It's direct experience photons from elsewhere entering your eye or striking your camera sensor. The universe becomes tangible in that moment. The coming weeks represent the peak opportunity for amateur observation. As 3i Atlas approaches its December 19th closest approach to Earth, at approximately 270 million kilometers, about 1.8 astronomical units, it will be well positioned in the pre-dawn sky for Northern Hemisphere observers. The Moon will be moving into new phase in mid-December, providing dark skies without lunar interference. And if the comet continues brightening, or maintains its current brightness, as some preliminary data suggests it might, it could become even more accessible to smaller telescopes and possibly strong binoculars. This is the moment amateur astronomers have been anticipating since the comet's discovery in July. The geometry is favorable, the timing is right, the equipment is ready. And around the world, people are setting their alarms for the pre-dawn hours, heading out into the cold with thermoses and star charts, joining a tradition as old as human curiosity. Because ultimately, amateur astronomy isn't about competing with professional institutions. It's not about discovering the next comet or planet, though those moments happen and are celebrated.
It's about participating directly in the cosmic story, about feeling connection to something larger than human affairs, about looking up and wondering. 3i Atlas doesn't discriminate. It reflects sunlight toward Earth with equal indifference, whether that light enters a billion-dollar space telescope or a small backyard refractor. And in that indifference is a kind of democracy. The universe is accessible to anyone willing to make the effort to observe it. Every amateur image of 3i Atlas adds to the record. Every observation contributes a data point. Professional astronomers welcome this contribution. More observations from more locations, at more times, creates a more complete picture. Science benefits from distributed networks of observers, from crowdsourced data collection, from the passion and dedication of people who pursue astronomy, not for career, but for love of the cosmos. And there's something moving about that. The comet, ancient and alien, passing through our neighborhood, for the first and only time being witnessed not just by experts, but by anyone with curiosity and a telescope. Witnessed, documented, pondered, appreciated. Future generations, if they maintain interest in astronomy, will look back at our observations of 3i Atlas. They'll see what we captured, what we understood, what puzzled us. And they'll recognize in our efforts the same impulse that drove ancient Babylonians to record comets on clay tablets, the same wonder that motivated the Maya to track celestial wanderers, the same curiosity that is humanity's defining characteristic. We watch because we wonder. We wonder because we're human. And 3i Atlas, by simply existing and passing within range of our instruments, gives us something wonderful to wonder about. Science progresses by proposing explanations for observations and testing those explanations against evidence. When observations don't fit existing models, when anomalies appear, we develop hypotheses to explain them. And for 3i Atlas, with its multiple anomalies clustering together, we need hypotheses. Plural. Because one anomaly might be explained simply, but multiple anomalies interacting demand careful, systematic thinking. Let me present 3 tiers of explanation for what we've observed with 3i Atlas. Each tier has different levels of supporting evidence, different degrees of speculation, different implications if true. This is how science works. We don't jump to the most sensational explanation.
We examine the most probable first, then consider progressively less likely but still possible scenarios, always guided by evidence and constrained by physical laws. Hypothesis 1: natural but unexpected. This is where most scientists focus their attention because it requires the fewest assumptions and invokes only known physical processes. The idea 3I Atlas is a natural comet, but its specific composition structure or formation history creates behavior that deviates from typical solar system comets while remaining entirely within the bounds of physics. The delayed water ice activation model sits at the center of this hypothesis. Here's how it works in detail. Comets contain multiple types of ices with different sublimation temperatures. Carbon dioxide ice sublimes at about -78 degrees Celsius. Water ice requires 0 degrees to melt somewhat higher to sublimate directly to vapor. Methane, carbon monoxide, ammonia each has its own characteristic temperature at which it transitions from solid to gas. As 3I Atlas approached the Sun from the cold depths of interstellar space, carbon dioxide would have begun sublimating first at large distances where temperatures remained very cold. Observations confirmed this. The comet showed a carbon dioxide-rich coma detected spectroscopically months before perihelion.
Now here's the key: sublimation is endothermic. It absorbs heat. When carbon dioxide transitions from solid to gas, it pulls thermal energy from the surrounding material. This creates a cooling effect similar to how evaporating sweat cools your skin. The sublimating carbon dioxide can actually keep nearby water ice frozen even as the comet approaches closer to the Sun and solar heating intensifies. Picture layers within the nucleus. Surface regions rich in carbon dioxide sublimate, vigorously creating an insulating layer of gas and a cooling effect that prevents underlying water ice from heating up. The water ice remains frozen dormant, not contributing to outgassing. But eventually, the solar heating becomes intense enough to overwhelm the cooling effect. At perihelion, when the comet receives maximum solar radiation, temperatures finally exceed water ice's sublimation threshold. When water ice finally does begin outgassing, it does so suddenly in a burst because so much of it has been kept artificially cold by the carbon dioxide shielding. This sudden release of water vapor along with the dust particles water ice carries when it sublimates creates the rapid brightening we observed. The brightness surge isn't from gradual increasing activity, but from a delayed activation, a threshold being crossed all at once rather than gradually. And here's where the missing tail might be explained. If the water ice activation happens very close to perihelion when the comet is moving at maximum speed, through the hottest zone, the sublimated water and ejected ice fragments don't have time to travel far before either vaporizing completely or dispersing so broadly they don't form a visible concentrated tail. The material is there being released, but it's dispersing rapidly in all directions rather than forming the characteristic rearward streaming tail we expect. This model explains several observations simultaneously. The carbon dioxide detected months before perihelion check, the rapid brightening near perihelion check, the lack of prominent dust tail potentially check if the timing and dispersion dynamics work out correctly. It also explains the unusual color progression. Red in July from organic-rich surface materials, green in September from carbon dioxide and dicarbon emissions as that ice sublimated, blue near perihelion from ionized molecules when water finally began outgassing vigorously and solar UV radiation ionized the gas molecules, creating blue fluorescence. The non-gravitational acceleration fits this model too. Asymmetric outgassing from active regions as water ice finally activated would create thrust, pushing the comet in directions not aligned with the radial solar direction, producing the measured trajectory changes. This hypothesis requires nothing exotic. Just normal cometry physics playing out in an unusual sequence because of the comet's specific composition, high carbon dioxide, low water, and its high approach velocity leading to rapid temperature changes.
Supporting this hypothesis are the compositional measurements. JWST detected the carbon dioxide dominance. Observations confirmed the unusual chemistry. The timing of different emissions aligns with different ices activating at different solar distances. It all hangs together coherently. What challenges this hypothesis? The main issue is quantitative. When researchers run detailed models, calculating how much water ice would need to sublimate to produce the observed brightening and how much gas should be visible, as a result, the numbers are tight. It's not clear the delayed activation model produces enough asymmetry in timing and enough rapid dispersion to fully explain why we see so little tail. Additionally, other comets have shown similar compositional mixes, high volatility, unusual ratios of different ices, and they still developed visible tails. So while the model is plausible, it needs refinement, more detailed calculations, perhaps some factors we haven't yet included. Still, this remains the leading natural explanation. It invokes only known processes. It accounts for most observations, and it makes testable predictions. As 3I Atlas continues moving away from the Sun, if water ice was indeed newly activated at perihelion, we should see continued activity for a while, as those freshly exposed ices continue sublimating. The light curve in December and January will help confirm or challenge this model. Hypothesis 2. Rare natural phenomena. Moving into less certain territory, this tier considers unusual but still natural processes that might occur. Rarely processes we haven't fully observed or understood because they're edge cases in cometry science.
One possibility: extreme cosmic ray processing. 3I Atlas spent billions of years in interstellar space, exposed constantly to galactic cosmic rays, high-energy particles that penetrate matter and alter its chemical and physical structure. Earth's heliosphere shields us from most cosmic ray flux, but in interstellar space, there's no shielding. The bombardment is relentless. Over billions of years, cosmic rays break down complex molecules, rearrange chemical bonds, implant foreign atoms, create radiation damage in crystalline structures. For a comet nucleus drifting through interstellar space for 7 to 11 billion years older than Earth, older than our Sun, the cumulative effect would be profound. The surface might develop an irradiated crust, a layer perhaps 10 to 20 meters deep, that's been chemically transformed from its original state. This crust might have unusual optical properties, absorbing and scattering light differently than normal cometary material.
It might have unusual mechanical properties, being harder or more porous than typical comet material, and it might respond to solar heating in unexpected ways. If the crust is unusually efficient at conducting heat inward, for instance, it might trigger subsurface outgassing that doesn't break through to form visible jets. Or if it's very porous, gas might escape diffusely, rather than in concentrated streams, creating activity that's hard to observe directly. JWST observations hinted at this deep radiation processing. The carbon dioxide abundance, the specific isotopic ratios detected, these suggest alteration during the comet's interstellar journey. But we're still learning what billions of years of radiation does to ices and rocks. This is frontier science hypotheses based on extrapolation from laboratory experiments and theoretical models, rather than direct observation of ancient irradiated comets. Another rare phenomenon: subsurface structure complexity. What if 3I Atlas isn't a simple solid nucleus, but has complex internal structure, voids, chambers, regions of different composition? Perhaps ancient impacts during its time in its home planetary system created fractures and voids. Or perhaps it's a contact binary, two objects weakly bound together with a gap between them. Or it could have differentiated partially, with denser material sinking toward the center and lighter ices concentrating in outer layers. Such complexity could create unusual outgassing patterns. Gas released from subsurface regions might travel through internal channels before escaping, emerging from locations not directly heated by the sun. This could create thrust not obviously correlated with the sun's direction, explaining non-gravitational acceleration without visible jets. The precedent exists. Comet 67P Churyumov-Gerasimenko, visited by the Rosetta spacecraft from 2014 to 2016, revealed extraordinarily complex morphology.
It's a contact binary, two lobes connected by a narrow neck. Its surface showed cliffs, pits, layered terrain, active regions emitting jets from specific locations. The complexity was far beyond what telescopic observations from Earth had suggested. If 3I Atlas has similar or even more extreme internal complexity developed over billions of years, under conditions different from solar system comets, its behavior might deviate significantly from models based on homogeneous nuclei. There's also the possibility of magnetic interactions. Some recent research suggests that comets might interact with the sun's magnetic field and the solar wind's embedded magnetic fields in more complex ways than previously appreciated. If 3I Atlas has unusual magnetic properties, perhaps from metal-rich regions within the nucleus, or from the effect of cosmic ray bombardment creating magnetic anomalies, it might interact with solar magnetic fields in ways that affect its trajectory or its coma's appearance. This is speculative. We have limited data on cometary magnetism, but it's not impossible, and it would be a natural phenomenon even if rare and poorly understood. Another consideration: rotation and shape. If 3I Atlas has an unusual rotation state, tumbling chaotically rather than spinning smoothly or rotating very slowly, or oriented such that different hemispheres experience vastly different solar heating, this could create asymmetric activity that appears unusual from our viewing perspective. Combined with an elongated or irregular shape, rotation could cause brightness variations, apparent morphological changes and activity patterns that seem strange until we account for the three-dimensional geometry. All these possibilities fall under natural phenomena, but rare, unusual, not well represented in our current database of observed comets. They're harder to test because we have fewer examples to compare against, but they remain within the bounds of known physics and chemistry.
Hypothesis 3. The technological speculation. Now we enter highly speculative territory. Let me be absolutely clear, this is not the leading explanation. There's no direct evidence supporting it, but the scientific method requires considering all possibilities that fit observations, even unlikely ones, as long as we acknowledge their speculative nature and don't elevate them prematurely. Avi Loeb has been the most prominent voice suggesting that 3I Atlas warrants investigation for possible technological origins. His argument rests on the accumulation of anomalies rather than any single smoking gun observation.
List of unusual characteristics: no significant tail despite perihelion passage, rapid brightening exceeding typical cometary rates, blue color near perihelion, bluer than the sun, non-gravitational acceleration without obvious outgassing, central bright light source of unclear origin, low water content 4 or 5% unusual for active comets, apparent structural stability through perihelion, course change without visible mechanism.
Individually, each anomaly might be explained naturally, as we've discussed, but collectively the pattern is unusual enough to warrant asking, if this weren't a natural comet, what might it be? The comparison to Oumuamua is relevant. That object showed non-gravitational acceleration without visible coma. Or tail had an extreme elongated shape, or possibly flat, like a disk tumbled in unusual ways and accelerated away from the sun faster than gravity alone predicted. Some researchers proposed it might be a light sail, a thin reflective surface pushed by solar radiation pressure, potentially artificial. The scientific community largely rejected that interpretation for Oumuamua, favoring natural explanations like outgassing hydrogen ice or unusual comet structure. But the debate established that asking the question isn't unscientific. It's legitimate to investigate whether observed phenomena might have technological origins, as long as you apply the same rigor to that hypothesis as to natural ones. For Three-Eye Atlas, the technological speculation centers on several observations. The blue color could indicate artificial lighting or hot propulsion systems rather than natural molecular emissions. The non-gravitational acceleration could represent controlled thrust rather than outgassing. The lack of visible tail could mean the object isn't primarily ice at all, but something else, metal, ceramic, composite materials that doesn't sublimate under solar heating. The central bright light particularly intrigues Loeb. In his public statements, always careful to note he's speculating, he's asked what natural process creates a concentrated bright source without corresponding extended gas and dust clouds. Ionized molecules fluoresce, yes, but in extended regions, not point sources. Reflected sunlight from a nucleus should appear as reflected sunlight solar spectrum, not significantly altered in color. If, and this is a massive if, Three-Eye Atlas were artificial, what might it be? Not a spacecraft in the sense of having astronauts aboard, presumably. The radiation environment of interstellar space would be lethal to biological organisms over billion-year timescales. But possibly a probe, a robotic explorer sent by some civilization long ago, drifting through the galaxy on automatic protocols, perhaps activating when approaching stars. Science fiction has explored these concepts extensively. Arthur C. Clarke's Rendezvous with Rama described a massive cylindrical alien vessel passing through the solar system, behaving in ways that initially puzzled human observers before its artificial nature became clear. The novel captured that sense of encountering something genuinely alien, something operating on principles and purposes beyond human understanding. But science fiction isn't science. The key question isn't whether we can imagine artificial scenarios, but whether evidence requires them. And currently, evidence doesn't require technological explanations. Natural explanations, while incomplete, remain viable. The gaps in our understanding are significant but not insurmountable. Loeb's position, as I understand it from his public statements and papers, is that we shouldn't dismiss the technological possibility prematurely. He argues that scientific conservatism, the tendency to favor conventional explanations, can sometimes prevent us from recognizing genuinely revolutionary discoveries. If we approach every anomalous object assuming it must be natural, we might miss the one that isn't. His critics counter that extraordinary claims require extraordinary evidence, and current observations of Three-Eye Atlas don't meet that threshold. They argue that proposing artificial origins based on incomplete understanding of natural phenomena is premature and potentially misleading to public discourse. Both positions have merit. Science benefits from bold thinkers, willing to propose unconventional ideas. It also benefits from skeptical gatekeeping that prevents speculative ideas from being treated as established fact prematurely. The tension between these forces drives progress.
What would constitute strong evidence for artificial origin? Several things, none of which we currently observe. Clear geometric regularity, sharp edges, right angles, symmetric structures inconsistent with natural formation, emission spectra, inconsistent with any natural chemistry, spectral lines from exotic elements or artificial compounds, deliberate trajectory, changes, course corrections, not explainable by outgassing or gravitational perturbations, communication signals, electromagnetic emissions with structured information-carrying patterns, materials or structures incompatible with natural processes, composites, manufactured alloys, engineered configurations.
We see none of these with Three-Eye Atlas. The anomalies we observe are quantitative, too bright. Wrong color, missing tail, not qualitative. They're matters of degree, not kind. That's an important distinction. Still, the question lingers because the pattern is unusual. Multiple anomalies clustering on one object creates a statistical argument that something genuinely different might be happening. But statistics don't prove mechanisms. They suggest where to look carefully, where to apply scrutiny. The responsible scientific approach is to pursue natural explanations vigorously while remaining open to evidence that might challenge them. Don't assume artificial origin. Don't rule it out absolutely either. Follow the data and acknowledge uncertainty. This is crucial. When we don't fully understand something, the honest statement is, we don't know yet, not it must be X, or it can't be Y. 3i Atlas presents genuine puzzles. The explanations remain incomplete. More observations, more analysis, more time to think and model. These will clarify the picture. The coming months offer opportunities. December observations when the comet is closest to Earth. March 2026, Jupiter encounter, ongoing tracking of trajectory, brightness, spectroscopy. Each data set adds constraints, narrows possibilities, potentially resolves anomalies. And probably the final answer will be natural. A comet with unusual but explicable properties formed around a different star in a different era, behaving strangely because we've never encountered quite this specific combination of factors before. That would still be fascinating, still teach us about interstellar chemistry and cometry science. Or maybe the anomalies will persist, will resist natural explanations, even as our models become more sophisticated. That would be genuinely interesting, would demand we consider possibilities we're currently treating as remote. Either way, the process of investigation, of proposing and testing hypotheses, of following evidence wherever it leads, that's science functioning as it should, not providing premature certainty, but pursuing understanding systematically and honestly. Step back from 3i Atlas specifically for a moment. Consider what its existence tells us about the galaxy, regardless of how we ultimately explain its unusual behavior. First, interstellar objects are real and detectable. Before Oumuamua in 2017, we had strong theoretical reasons to expect interstellar visitors. Every planetary system should eject some material during its formation and evolution. Jupiter-sized planets gravitationally scatter smaller bodies, some of which achieve escape velocity and leave their home systems entirely. Multiply this process by hundreds of billions of stars across billions of years, and the galaxy should be full of wandering objects, planets, asteroids, comets drifting through interstellar space. But theory and observation are different. Until we actually detected an interstellar visitor, we couldn't be certain our theories were correct. Oumuamua confirmed, yes, they exist. 2i Borisov confirmed they're not extremely rare. 3i Atlas confirms we should expect them regularly. Statistical analysis based on these three detections suggests that at any given moment, several interstellar objects are passing through our solar system. Most go undetected because they're too faint, too far from the sun to become active or oriented such that our surveys miss them. We're seeing the tip of the iceberg. What does this mean practically? It means the solar system isn't isolated. We exist in a galactic environment where material circulates between star systems. The boundary between our stuff and their stuff is porous. Matter flows through, carrying information about other stellar neighborhoods, other planetary systems, other formation conditions.
This has implications for astrobiology. The panspermia hypothesis, the idea that life might spread between planetary systems via material transfer, has been around for over a century. Usually it's discussed in terms of impact ejection. A large asteroid hits a planet, launching rocks into space, some of which eventually reach other star systems. If those rocks contain hardy microorganisms, perhaps life could spread this way. But interstellar comets offer another vector. Comets contain organic molecules, water, sometimes complex chemistry. If they can carry this material between star systems And if life can survive in dormant states for millions of years of interstellar transit, then comet-mediated panspermia becomes plausible. We don't know if Triasis carries organic compounds. Spectroscopic observations have focused on gases in the coma: carbon dioxide, water, carbon monoxide.
Detecting more complex organics requires different techniques, higher spectral resolution, or direct sampling. But other comets contain amino acids, nucleobases, complex carbon chains. There's no reason interstellar comets couldn't carry similar cargo. If they do, and if microorganisms or even just prebiotic chemistry can survive the journey, then life in the galaxy might be more interconnected than we typically imagine. Not all life on Earth necessarily arose here. Some might have arrived from elsewhere, delivered by ancient impacts or gentle accretion of interstellar material. This isn't New Age mysticism. It's serious scientific speculation grounded in our growing understanding of how hardy life can be, how thoroughly material mixes in protoplanetary disks, and how permeable the boundaries between stellar systems are. Ancient cultures intuited this interconnection in their mythologies. Hindu cosmology speaks of endless cycles of creation and destruction on cosmic scales, of consciousness pervading the universe. The idea that Earth isn't isolated, that we're part of a larger whole, appears across traditions. Egyptian mythology depicted the sky goddess Nut swallowing the sun each evening and giving birth to it each morning, a metaphor for cyclical processes for material moving through different states. The scarab beetle rolling the sun across the sky represented transformation movement, cosmic fertilization. These weren't scientific models in our sense, but they captured an intuition: the Earth participates in larger cosmic processes. We're not separate from the heavens. We're made of the same stuff, subject to the same forces, connected by flows of matter and energy. Modern science confirms this, but with specifics. We know that heavy elements in our bodies, carbon, nitrogen, oxygen, iron, were forged in stellar cores and scattered by supernovae. We are literally made of stardust atoms that cycled through stars that lived and died before our sun formed. Adding to that picture, we now know that intact objects circulate between star systems, potentially carrying not just atoms, but molecules, chemistry, maybe information about conditions elsewhere. The cosmos is a web of connections, not a collection of isolated islands. This reframes questions about life's origin. Maybe the right question isn't, how did life begin on Earth, but how did life begin in this region of the galaxy? And how did it spread among emerging planetary systems? Earth's specific chemistry might be more cosmopolitan than we thought, influenced by materials that formed around other stars. Consider the Drake equation, that famous formula for estimating the number of communicative civilizations in the galaxy. One term in the equation is the fraction of planets where life actually develops. Traditional thinking treats each planet as an independent experiment. Life either arises or doesn't, based on local conditions. But if panspermia operates, planets aren't independent. They're connected through material exchange. Life arising once in a given region might seed multiple planetary systems. The fraction of planets with life could be higher than independent origin calculations suggest. Conversely, civilizations might be more interconnected than we assume. Advanced species might seed their stellar neighborhoods deliberately or accidentally, with microorganisms, with self-replicating probes, with information encoded in durable materials. The galaxy could be more thoroughly connected than our models assume. These are speculations, but they're grounded in the confirmed fact that material does transfer between stars. The 3 interstellar objects we've detected prove that. How common such transfers are, what materials they carry, whether they affect planetary biology or even carry deliberate messages, these remain open questions. But 3i Atlas contributes to this evolving understanding simply by existing and being observable. Every interstellar visitor we study adds data points, constraints. Models, refines our understanding of galactic ecology. There's also a humbling perspective here. 3I Atlas formed 7 to 11 billion years ago, probably around a star that no longer exists. That star lived its life, perhaps, formed planets. Perhaps those planets developed life or civilizations, and then the star died, possibly in a supernova or planetary nebula, scattering its materials into space. Some of those materials, perhaps including our visitor, escaped into interstellar space and have been wandering ever since. For billions of years, 3I Atlas traveled through the galaxy. It might have passed dozens or hundreds of other star systems, always too far away to be captured, always maintaining its hyperbolic trajectory through each stellar encounter. It witnessed the Milky Way evolve, saw new stars born from collapsing molecular clouds, old stars die in various spectacular or quiet ways. And finally, after all that time, its trajectory happened to intersect our solar system during the brief cosmic moment when a technological species US exists here with the capability to detect and study it. That coincidence, that intersection of timescales and space, is remarkable. We exist in the right era to observe interstellar visitors. A few centuries earlier, we wouldn't have had the technology. A few centuries later, assuming our civilization persists, we'll have better technology, space-based telescopes, with higher resolution, perhaps spacecraft capable of intercepting these visitors for direct study. But now, in this particular window of human development, we can detect them, analyze them from afar, and wonder about them. The window is narrow in another sense, too. 3I Atlas will be observable for mere months before it recedes beyond detection thresholds. By this time next year, it will be gone, moving back into interstellar space, heading toward whatever stellar encounters await it over the next billion years. This is our moment with it, the only time in human history we'll have this particular visitor within reach of our instruments. That sense of finality adds weight to every observation. There's no second chance, no follow-up mission we can plan for 20 years hence when technology improves. Now is the time. These months, these observations, this data set, it's all we'll ever have of 3I Atlas, and yet more visitors will come. Statistical models now suggest we should detect several interstellar objects per year once our survey capabilities improve. The upcoming Vera Rubin Observatory, with its large mirror and wide field of view, will scan the sky repeatedly, detecting faint moving objects that current surveys miss. It should find many more interstellar visitors, perhaps dozens per year. Each will be unique, formed in different stellar systems, carrying different chemistry, offering different insights. Some might be more obviously cometary than 3I Atlas. Others might be inactive asteroids, dark and cold, detectable only by reflected sunlight. Perhaps we'll detect a genuinely bizarre object that challenges our categories entirely. The future of interstellar object studies is bright. We're at the beginning of this field, not the end. 3I Atlas is the third known visitor, but it won't be the last by any means. We're learning how to detect them, what instruments work best, what observations are most scientifically valuable, how to mobilize the global astronomical community rapidly when a new visitor appears. Each detection teaches us. Each data set refines models. And gradually interstellar visitors will transition from exotic anomalies to routine objects of study, each contributing to our understanding of the galaxy's population of wandering bodies. But 3I Atlas will always be special as the third, the one that behaved strangely, that presented puzzles that made astronomers scratch their heads and propose competing explanations. The one that captured public imagination, that sparked debates about transparency and speculation, that became briefly a cultural phenomenon. And the one that's visible right now to anyone with a telescope and curiosity, offering direct participation in this cosmic moment. December 19th, 2025. Mark that date. It represents the climax of our observation window, the moment when 3I Atlas passes closest to Earth, approximately 269 million kilometers or 1.8 astronomical units. Not close by cosmic standards, still much farther than Mars at its closest approach, but as close as this visitor will ever be to our planet. The geometry is favorable. By mid-December, the comet will be rising several hours before the sun for Northern Hemisphere observers, high enough in the sky that atmospheric interference is minimal, dark enough that the pre-dawn darkness provides excellent contrast. The moon will be in new phase, removing that source of light pollution, weather permitting. And that's always the astronomer's caveat: conditions will be nearly ideal. Professional observatories are scheduling observations with unprecedented coordination. The Hubble Space Telescope, which captured detailed images of 3I Atlas in July when the comet was 277 million miles from Earth, has additional observations planned for December at closer range. With the comet potentially still active from perihelion, Hubble should resolve coma structure in extraordinary detail. If the nucleus is large enough and the coma has thinned sufficiently, we might even see the nucleus itself as a distinct point within the fuzzy glow. The James Webb Space Telescope continues its near-infrared spectroscopy campaign.
Webb's earlier observations in August detected carbon dioxide, water, and carbon monoxide in the coma. Follow-up observations in December will track how these abundances evolve as the comet moves away from perihelion. Are carbon dioxide emissions decreasing as expected for a more volatile ice? Is water emission increasing as delayed activation continues? Are there new molecules appearing as different temperature regimes expose different ices? Every data point helps constrain models of the comet's composition and behavior.
The evolution of the spectrum over time tells a story about the nucleus's layered structure, about how solar heating penetrates and affects different depths, about what chemistry occurs in the coma as molecules interact with solar radiation. Ground-based observatories worldwide are participating. The Keck Observatory in Hawaii, one of the world's largest optical telescopes, will obtain high-resolution spectra. The Very Large Telescope in Chile, with its collection of large instruments, will conduct multi-wavelength observations. The Gemini telescopes, both north and south, continue their monitoring program, tracking brightness, coma, morphology, and activity levels. Radio telescopes are also involved. While 3I Atlas doesn't emit radio waves itself, radio observations can detect specific molecules through their characteristic radio frequency emission lines. The Atacama Large Millimeter Array ALMA might detect rare molecules that optical telescopes cannot observe, providing additional clues about the comet's chemistry. This coordinated campaign represents modern astronomy at its best. Instruments around the world and in space, each with different capabilities, all focusing on a single target. The data will be shared among research teams, analyzed, collectively published in open access forums where the global scientific community can evaluate and build upon it. Amateur astronomers are fully engaged as well. Online communities have organized observation campaigns where individuals at different longitudes coordinate to provide nearly continuous coverage. When sunset arrives in North America, observers in Europe are already in darkness beginning their sessions. As European skies brighten with morning twilight, Asian observers continue the coverage. The global relay provides temporal resolution that no single observatory can match. The quality of amateur images has been steadily improving as observers refine their techniques and share insights. Some of the best amateur astrophotographers, using equipment costing thousands rather than millions of dollars, produce images rivaling professional observations from decades past. Image processing techniques, once proprietary professional tools, are now available as open-source software that anyone can master with practice. This democratization of observation creates a participatory science that engages public interest in ways institutional astronomy cannot achieve alone. When someone captures 3I Atlas through their own telescope processes, their own images shares them with a community that appreciates the effort. They're not passive consumers of science, but active participants. That engagement matters for science literacy, for maintaining public support, for astronomical research, for inspiring the next generation of professional astronomers. The December approach tests several hypotheses about 3I Atlas. If the comet lost massive amounts of material during perihelion, as some models suggest, based on the rapid brightening December observations, should reveal a large debris cloud. This cloud would scatter sunlight, appearing as an extended halo around the nucleus. The size and density of this debris field would directly constrain how much material was actually ejected. Conversely, if no substantial debris cloud is detected, that would argue against simple outgassing explanations for the brightening. It would push researchers toward more exotic interpretations. Maybe the brightening resulted from something other than mass ejection, perhaps changes in surface properties that affected reflectivity, or perhaps gas emissions without accompanying dust. The trajectory data from December is crucial for understanding non-gravitational acceleration.
Precise astrometric measurements tracking the comet's exact position against background stars using multiple observations over weeks will show whether the trajectory matches predictions based on perihelion outgassing or whether additional forces are acting. Any discrepancy between predicted and observed positions would be highly significant. If the comet is where gravitational models plus measured perihelion outgassing predict, that validates our understanding. If it's somewhere else, even slightly, that demands explanation. And explanations matter because trajectory prediction is how we rule out collision hazards, how we plan future observations, how we understand the physics governing small body dynamics. The visibility to amateur equipment means citizen scientists can contribute to this astrometry.
A coordinated network of amateur observers, each carefully measuring the comet's position in their images and reporting it to central databases like the Minor Planet Center, provides data density that professional surveys can't match. More measurements from more locations at more times create a more robust data set, reducing uncertainties and potentially detecting subtle effects that sparse data might miss. From a human perspective, December brings the culmination of this story's public-facing arc. The comet will be as accessible as it's going to get. Media coverage will peak. Amateur astronomers who've been following the story since July will have their best opportunity to observe. Schools and planetariums will host viewing events when scheduling and weather permit. This is the moment 3I Atlas transitions from thing professional astronomers study to thing I saw with my own eyes. That transition matters psychologically. Reading about an interstellar visitor is intellectually interesting. Seeing it directly, even as a faint, fuzzy patch requiring careful observation, creates an emotional connection that reading cannot replicate. That emotional connection serves science well. People who feel connected to astronomical phenomena are more likely to support funding for observatories, more likely to encourage children's interest in STEM fields, more likely to value scientific inquiry as a societal good. These aren't trivial benefits. They're foundational to maintaining the infrastructure and culture that makes astronomical research possible. After December 3rd, Atlas continues its journey outward. The next major milestone is March 16, 2026, when it passes approximately 53 million kilometers from Jupiter. That flyby offers additional observation opportunities. NASA's Juno spacecraft currently orbiting Jupiter could potentially observe the comet if NASA approves a mission extension. Congresswoman Luna's advocacy for this observation continues, though budgetary and operational decisions rest with the agency. Jupiter observations would be valuable for several reasons. The comet will be in a different state than during the Mars flyby or the December Earth observations. By March, it will have moved significantly farther from the Sun, and its activity level should have changed accordingly. How it changes, whether it fades rapidly, maintains steady state, or shows unexpected behavior, tells us about its composition and structure. Jupiter's environment is unique. The planet has powerful radiation belts and a strong magnetic field. If the comet's coma interacts with this environment in observable ways, that interaction reveals properties of the coma and nucleus we couldn't measure otherwise. Does the magnetic field shape the ion tail? Do Jupiter's radiation belts ionize coma molecules differently than solar UV does? Can we detect any gravitational perturbation from Jupiter affecting the trajectory? The European Space Agency's JUICE spacecraft. Jupiter, Icy Moons Explorer, is also in flight toward Jupiter with arrival planned for 2031. JUICE conducted observations of 3I Atlas in November 2025 during its cruise phase, though the data won't be transmitted back to Earth until February 2026 due to the spacecraft's distance and limited data transmission bandwidth. Those observations will provide another viewing angle, another set of instruments, another data point in the evolving story. After Jupiter 3I Atlas heads into the outer solar system, it will pass the orbits of Saturn, Uranus, Neptune over the following years, though it will be far too faint for observation by then. Eventually, perhaps a few years from now, it will cross the heliopause, the boundary, where the solar wind gives way to the interstellar medium and officially return to interstellar space. Its journey continues indefinitely. In tens of thousands of years, it might pass near another star experience, another perihelion perhaps, activate again if that star is bright enough. Or it might wander for millions of years between stellar encounters, cold and dormant, carrying its cargo of ancient ices through the galaxy's spiral arms, a messenger unread, a time capsule unopened. We'll never know where it goes. Our observations end when it fades beyond detection thresholds, and that's final. No future mission will chase it down. The speeds involved make interception impossible with current or near-future technology. This is genuinely goodbye, not see you later. That finality should focus our attention on the present opportunity. These weeks in December, these observations were gathering this moment of human-comet interaction. It's all we get. Make the most of it. If you have access to a telescope, observe. If you have processing skills, contribute. If you have curiosity, learn. Because moments like this are why we do astronomy. Not for practical benefits, though those exist. Not for technological spin-offs, though those occur. We do astronomy because we're curious, because we want to understand our place in the cosmos, because looking at the universe and trying to comprehend it is fundamentally human. 3I Atlas is billions of years old. It formed when the universe was younger, in a galaxy with fewer heavy elements around a star that might have been very different from our sun. It carries information about cosmic dawn, about early stellar generations, about planetary formation in conditions we can only infer from models. And for a brief moment measured in months, it's within reach of our instruments. We're capturing its light, analyzing its chemistry, tracking its motion. We're learning from it. And through that learning, we're connecting across space and time to processes that shaped the galaxy billions of years before Earth existed. That's profound. That's worth the cold pre-dawn observations, the careful data reduction, the meticulous analysis, the public outreach to share these findings. Because this is what intelligence does. It reaches out, it observes, it tries to understand. December 2025 is our time with 3I Atlas. After that, the comet recedes, the observations become more difficult, the public attention moves elsewhere. But the data will remain. The images, spectra, trajectory measurements, these become part of humanity's astronomical record available to future researchers who might have better theories, better models, better understanding of what we were seeing. And maybe they'll look back and realize we missed something obvious, misinterpreted some crucial observation. That's fine. That's how science progresses. Or maybe they'll confirm our interpretations, validate our models. Add 3I Atlas to the catalog of understood objects. That's fine too. Either way, we're building knowledge. Each observation adds to the foundation. Each paper refines understanding. Each conversation, each debate, each hypothesis proposed and tested at all contributes to the slow, steady accumulation of insight that defines scientific progress. So December approaches. The comet climbs higher in the pre-dawn sky. Telescopes around the world prepare. Amateur astronomers check their equipment plan, their sessions hope for clear skies, and humanity collectively focuses its attention for this brief window on a visitor from the stars. This is astronomy at its most exciting.
Not the routine survey work, not the long-term monitoring programs, but the unexpected visitor demanding attention, presenting puzzles, offering discovery. This is why we build observatories, why we train astronomers, why we maintain this global infrastructure of instruments and expertise. For moments like this, for 3i Atlas, for the chance to see beyond our solar family into the broader galactic neighborhood and glimpse what else is out there wandering the void, occasionally passing close enough to study. Let's be honest about what remains unexplained. After months of observation, after analysis by dozens of research teams, after papers published and hypotheses proposed, 3i Atlas still presents genuine mysteries. It's important to acknowledge this clearly rather than pretending we understand more than we do. The tail remains the central puzzle.
Why didn't 3i Atlas develop a visible tail comparable to other comets at similar solar distances? The delayed water ice activation hypothesis offers a framework, but the quantitative details remain uncertain. Models haven't definitively shown that the timing and dispersion dynamics work out to produce the observed lack of tail while simultaneously producing the observed brightness. Spectroscopic observations confirmed gas emissions, carbon dioxide, water, carbon monoxide. Where did those gases go? Gas molecules don't disappear. They expand into space, get pushed by solar winds, scatter sunlight, or fluoresce when ionized. That material should be visible as an extended structure. Yet post-perihelion images show compact morphology without prominent extensions. Perhaps the viewing geometry played a role. Maybe we're seeing the comet at an unfortunate angle where a tail exists but projects toward or away from our line of sight, making it difficult to detect against the bright inner coma.
But other observers from different perspectives, the Mars orbiters, the space-based solar observatories during perihelion, should have seen it from different angles if it existed. Or perhaps the tail is there, but extremely diffuse, spread over such a large area that its surface brightness falls below detection thresholds in most observations. This is possible, but it raises questions about why the material dispersed so broadly, rather than forming the concentrated streams we normally observe. The central bright light source remains unexplained. Post-perihelion images show a concentrated bright region within the coma. Standard interpretation reflected sunlight from the nucleus, possibly enhanced by active regions or freshly exposed ices. But the persistence and intensity of this bright central region seem unusual compared to typical comets, where the nucleus is often difficult to distinguish from the surrounding coma. High-resolution imaging might resolve this.
If Hubble's December observations can isolate the nucleus as a distinct point, we can measure its true brightness and compare that to the surrounding coma. If the nucleus accounts for most of the central brightness, mystery solved. If not, if the brightness requires additional explanation, that's interesting. The non-gravitational acceleration puzzle continues. Yes, asymmetric outgassing can explain it, but seeing no obvious outgassing jets while detecting course changes creates a mismatch between prediction and observation. Maybe the outgassing occurs from regions we can't see from our viewing angle. Maybe it's diffuse rather than concentrated in jets, making it hard to observe while still providing thrust. Maybe internal structure channels gas in unexpected ways. These are plausible scenarios, but they remain scenarios rather than confirmed explanations. Precise trajectory tracking in December and beyond will help. If the non-gravitational forces continue in predictable ways, correlated with solar distance that supports outgassing models. If the forces behave erratically or cease suddenly, that suggests something more complex about the comet's activity or structure. The rapid brightening near perihelion quantified as following a power law with exponent around negative 7.5 compared to the typical negative 2 to 4 demands better explanation. Why did 3I Atlas brighten so much more rapidly than comparable comets? The delayed activation hypothesis predicts rapid brightening when water ice finally activates. But does it predict brightening this rapid? Detailed models incorporating thermal physics, sublimation kinetics, the cooling effect of carbon dioxide ice, the specific geometry and rotation of the nucleus. These complex calculations might show that the observed brightening is consistent with natural processes, or they might show gaps, suggest additional factors we haven't considered. This modeling work is ongoing. It's difficult, requiring significant computational resources and detailed physics, but it's necessary if we want to claim we understand what happened. The blue color near perihelion sits in that uncomfortable space between explained and mysterious. Ionized molecules could produce it, yes, but the specific brightness and spectral characteristics need to match observed emissions quantitatively, not just qualitatively. Have we measured the emission lines with sufficient precision to confirm that ionized carbon monoxide or other ions account for the blue color? Or does the spectrum show something unexpected? These spectroscopic details matter. They're the difference between plausibly explained and definitely understood. And we're somewhere between those poles currently. The low water content, only 4 to 5%, is unusual but not unprecedented. Some solar system comets show low water abundance. What makes 3I Atlas interesting is the combination of low water with high carbon dioxide and the unusual behavior. It's the pattern, not any single characteristic. If we found another comet with similar composition behaving similarly, we'd start to understand this as a category: carbon dioxide-rich interstellar comets with specific behavioral characteristics. One example isn't enough to establish a category. We need more data points. Future interstellar visitors will help. Where did 3I Atlas originate? We can't answer definitively. Trajectory calculations traced backward through space show the general direction from which it arrived, but uncertainties compound over time and distance. Small gravitational perturbations from passing stars during its interstellar journey would alter its path unpredictably. We can't identify a specific home star system.
What we can say, it came from somewhere in the galactic disk, probably from a stellar population formed 7 to 11 billion years ago based on chemical signatures. That era saw different star formation rates, different supernova frequencies, different galactic dynamics than today. The stellar neighborhood was different. The distribution of heavy elements was different. The rate of planetary system formation might have been different. 3I Atlas is a sample of that ancient environment, but we can't visit its home, can't study the planetary system where it formed, can't know whether that system still exists or was long ago destroyed by its star's death throes. The age itself, 7 to 11 billion years, carries profound implications. Earth is 4.5 billion years old. Our sun is 4.6 billion years old. The oldest rocks we've found on Earth are about 4.4 billion years old. 3I Atlas predates all of this by billions of years.
It existed when the Milky Way looked different, when our sun hadn't yet formed, when the molecular cloud that would become our solar system was still just diffuse, gas scattered among the stars. What has 3I Atlas seen in that time? How many star systems has it passed? How close did it come to other stars, other planets? Was it ever temporarily captured into an orbit before escaping? Has it collided with other interstellar objects, broken apart and reaggregated? We can't know. The object carries no record of its journey accessible to our instruments. It's a time traveler with amnesia, unable to tell us where it's been. There's something profound in acknowledging these limits. Science isn't about achieving complete certainty. It's about pushing the boundaries of knowledge while honestly recognizing where those boundaries lie. We know more about 3i Atlas than we did in July. We'll know more in January than we know now. But we'll always have questions, uncertainties, gaps in understanding. Ancient mysteries demonstrate this principle. The Antikythera mechanism, that remarkable ancient Greek analog computer discovered in a shipwreck, took over a century to understand. Initial examinations couldn't determine its purpose. Decades of study gradually revealed it calculated astronomical positions. Modern X-ray tomography and computer modeling finally showed its full complexity. Dozens of interlocking gears predicting eclipses, tracking planetary motions, encoding sophisticated mathematical models of celestial mechanics. But even now, we don't know who built it, or why that level of technological sophistication apparently didn't spread beyond a few rare examples. The mechanism remains somewhat mysterious despite our understanding of its function. The Voynich manuscript, a 15th century book written in an unknown script illustrated with enigmatic drawings, remains undeciphered.
Cryptographers have tried for centuries. Computer analysis has attempted statistical attacks. The best conclusion is that it's either an elaborate hoax or a genuine document in a language or code we cannot crack with available information. Göbekli Tepe in Turkey, massive stone structures built around 9600 BCE, predating agriculture, predating settled civilization, rewrote our understanding of human social organization, but we still don't fully understand who built it, how they organized the labor, what rituals or purposes motivated such enormous effort by pre-agricultural peoples. These mysteries persist, not because we're incompetent, but because information has been lost, because historical record is incomplete, because some questions require data we don't have and can't obtain. 3i Atlas similarly might retain mysteries not because we're bad astronomers, but because the data we can gather from 270 million kilometers away using electromagnetic radiation has inherent limits.
We can't touch the object, can't sample it directly, can't see its far side or its interior, can't rewind its trajectory through billions of years with perfect precision. We work with what we have. We squeeze every bit of information from available observations. We build models constrained by those observations. We acknowledge uncertainty while pursuing understanding. This is the scientific method functioning as designed, not providing premature certainty, but systematically reducing uncertainty through observation and analysis. Each measurement narrows possibilities. Each test constrains models. Gradually, patiently, explanations emerge that fit available evidence. And sometimes those explanations revolutionize understanding. Heliocentrism overturned geocentric models. Relativity replaced Newtonian mechanics in extreme conditions. Quantum mechanics revealed counterintuitive truths about reality at small scales. Each revolution began with unexplained anomalies, observations that didn't fit existing frameworks. Is 3i Atlas that kind of revolutionary anomaly? Probably not. Most anomalies resolve within existing frameworks with refinement rather than replacement, but possibly. We won't know until we've pursued every natural explanation thoroughly and honestly. The scientific community is doing that. Papers are being published, hypotheses are being tested, models are being refined. This process takes time, years, typically not months. Rush to conclusions and you'll likely be wrong. Be patient, let evidence accumulate, let analysis mature, and you'll converge on truth even if slowly. So the unanswered questions remain for now. That's acceptable. That's normal. That's honest science acknowledging its limits while continuing to push against them. The questions motivate future work. They inspire the next generation of astronomers who will build better instruments, develop better models, observe the next interstellar visitor with refined understanding gained from 3i Atlas. Progress is iterative, each generation building on previous work. And there's something beautiful in that. We're part of a continuum extending from ancient Babylonian astronomers through Galileo and Newton to modern researchers and forward to future scientists not yet born, all sharing the fundamental human impulse to observe, understand, explain. 3i Atlas is one moment in that endless project, an important moment, a fascinating moment, but one moment among countless others. What we learn from it joins the accumulated wisdom of millennia. What we fail to learn motivates continued effort. The universe is patient. It doesn't demand we understand immediately. It simply exists, waiting for us to develop the tools and insights necessary to comprehend it. Sometimes that takes centuries.
Sometimes millennia, but gradually understanding deepens. We're privileged to live in an era when interstellar visitors become observable, when we have instruments capable of detecting and analyzing them. Previous generations couldn't do this. Future generations will do it better. But this is our moment, our contribution to the long project of cosmic understanding. And that's enough. We don't need complete answers immediately. We need to observe carefully, analyze honestly, share openly, and acknowledge both what we know and what we don't. That's good science. That's responsible inquiry. That's the foundation on which future understanding will be built. In the pre-dawn darkness of December 2025, across the Northern Hemisphere, people are setting alarms for hours earlier than they'd prefer. They're dressing warmly, gathering equipment, thermoses, star charts, cameras, telescopes, and heading outside while most of their neighbors sleep. They're going to observe 3i Atlas,
A fuzzy patch of light in the constellation Virgo, an interstellar visitor older than Earth passing through our neighborhood for the first and only time accessible to anyone with curiosity and a modest telescope. This moment connects us across multiple dimensions. Temporally, we connect to the past, to the moment 7 to 11 billion years ago when this object formed around a star that may no longer exist, to the billions of years it spent drifting through interstellar space, bombarded by cosmic rays occasionally passing near other stars but never captured, to the ancient astronomers who watched their own skies and wondered about wandering lights, to the continuum of human curiosity stretching back to our species' origin. Spatially, we connect across the galaxy. 3i Atlas is not from here. It formed elsewhere in conditions different from our solar system's, carrying chemistry from a different molecular cloud. Its presence in our sky represents a message from another part of the Milky Way matter that has traveled tens of thousands of light years over billions of years to arrive at this place at this time. Intellectually, we connect the specific to the universal. This one object informs our understanding of comet formation everywhere, of how planetary systems evolve, of how materials circulate through galaxies, from particular observations, spectra, brightnesses, trajectories. We build general theories applicable far beyond this single case. Emotionally, we connect to something larger than human concerns. In our daily lives, we focus on immediate problems, personal relationships, societal issues. But standing under a dark sky, observing an interstellar visitor, those concerns recede momentarily. We become aware of vast scales, deep-time cosmic processes indifferent to human existence, yet beautiful in their complexity. This is what 3i Atlas offers beyond its scientific data perspective.
a reminder that we're participants in a universe far older, larger, and stranger than everyday experience suggests. A chance to step outside our ordinary frame of reference and contemplate our place in this extraordinary cosmic story. What have we learned? Let's separate the confirmed from the speculative. Confirmed facts about 3i Atlas. It arrived from interstellar space on a hyperbolic trajectory, making it the third confirmed interstellar object detected passing through our solar system. Its speed and direction prove it's not gravitationally bound to the sun. It's an active comet with a visible coma composed of gases, including carbon dioxide, water, and carbon monoxide, confirmed by spectroscopic observations from multiple instruments. It underwent dramatic brightening as it approached the Sun, with the rate of brightening significantly exceeding typical cometry models based on solar system comets.
Post-perihelion observations revealed the comet lacks a prominent tail visible in most observations, which is highly anomalous for a comet that passed through perihelion experiencing intense solar heating. It exhibited non-gravitational acceleration trajectory changes beyond what gravity alone predicts, measured by precise orbital determination using multiple observations. Its chemical composition differs from typical solar system comets, particularly in having high carbon dioxide abundance and relatively low water content. Age estimates based on radiation processing suggest it's 7 to 11 billion years old, formed around a star in the early history of the Milky Way galaxy. These are facts supported by observational data and accepted by the scientific community, regardless of interpretive differences about their meaning. What remains speculative, the specific mechanism explaining why the tail failed to develop prominently. The delayed water ice activation hypothesis is plausible but not definitively confirmed through detailed modeling. The source of the central bright light and the blue coloration observed near perihelion. Natural explanations exist but require more quantitative confirmation. The internal structure of the nucleus, whether it's homogeneous, layered, fractured, or complex, in ways that affect outgassing patterns. The exact origin location in the galaxy. We know the general direction, but can't identify a specific home star system. Whether similar interstellar objects will show comparable behavior, or whether 3I Atlas represents a unique case requiring special explanation. Any technological interpretation. This remains highly speculative with no direct evidence supporting it, though some researchers argue the pattern of anomalies warrants investigation. The distinction between confirmed and speculative is crucial. Conflating them leads to misunderstanding. We can be confident about what we've observed while remaining uncertain about interpretations. That's not a flaw in the scientific process. It's the process functioning properly. Science builds knowledge incrementally. Observations accumulate, models refine, understanding deepens, but it happens gradually over years and decades, not instantly upon first encounter with something new. Decades from now, researchers will look back at our observations of 3I Atlas with more context. They'll have studied dozens or hundreds of interstellar visitors. They'll have better models of cometry behavior, refined understanding of interstellar chemistry, perhaps direct samples returned from interstellar objects by advanced spacecraft. From that future vantage point, 3I Atlas might appear as an interesting early example, its anomalies explained by factors we're only beginning to understand now, or it might remain genuinely unusual, a one-off case that pushed us toward discoveries we couldn't anticipate. Either way, our contribution is to observe carefully and document thoroughly, to gather the data that future researchers will analyze with better tools and theories, to ask honest questions and acknowledge uncertainties, to pursue understanding while respecting the limits of current knowledge, and to appreciate the profound strangeness of this moment. An object from another star system from another era of galactic history happens to pass through our cosmic neighborhood during the brief window when humanity has developed technology to detect and study it. That coincidence of space-time and capability is remarkable. If 3I Atlas had passed through 1 million years ago, no human eyes would have seen it except as a faint, fuzzy star if noticed at all. 1 million years hence, if humanity or its descendants exist, they'll have capabilities we can barely imagine. But now, in 2025, with our current level of technology, we're just capable enough to detect, track, and analyze this visitor. Not perfectly, not completely, but adequately to learn. That seems almost designed, though, of course, it's not. It's coincidence, the random intersection of independent processes. But coincidence that feels meaningful, that creates opportunity, that allows connection across cosmic distances. The ancient impulse to find meaning in celestial events isn't entirely misguided. Not meaning in the sense of divine messages or predetermined fate, but meaning in the sense of significance, of information, of opportunities to learn. Three-Eye Atlas is meaningful because it teaches us about the galaxy, about comet formation, about how different our cosmic neighborhood can be from what we're familiar with. Every culture throughout history has looked at comets and assigned significance. We're not different. We just express that significance in the language of science rather than mythology, through spectra and trajectories rather than omens and portents. But the underlying response is the same recognition that something unusual deserves attention. And maybe centuries or millennia from now, when interstellar travel becomes routine, when humanity or its descendants move among the stars, as easily as we now cross oceans, they'll remember Three-Eye Atlas as one of the early visitors that helped us understand the galaxy is full of wanderers. That material circulates between stellar systems, that the cosmos is connected, networked, a web of interactions rather than isolated islands. That understanding could shape how future civilizations think about themselves, about their place in the universe, about their relationship to other star systems and potentially other life forms. Three-Eye Atlas is part of the foundation for that future understanding. For now, though, the comet is simply there in the pre-dawn sky, visible to patient observers, with telescopes reflecting sunlight that left the sun 8 minutes ago to illuminate an object formed billions of years ago, billions of kilometers from here. That light, bouncing off ancient ices and dust, travels another 8 minutes to reach Earth, where it enters telescopes and eyes, creating tiny chemical reactions in light sensors or photoreceptors that our brains interpret as vision. Through that process, photons linking sun, comet, and observer, we participate in the cosmic network. We're not separate from what we observe. We're part of the same system, made of the same atoms, forged in stars, subject to the same physical laws, sharing the same galaxy. Three-Eye Atlas is our relative in that deep sense. Not literally, it didn't form from the same molecular cloud that became our solar system, but metaphorically, cosmically.
We're all products of the same galactic ecology, the same processes of stellar birth and death, planet formation and destruction, materials cycling through stars and spaces over eons. Recognizing that kinship doesn't require mysticism. It's simply acknowledging physical reality, the interconnectedness that chemistry and physics create across space and time. We're made of recycled stardust, so is Three-Eye Atlas. That connects us fundamentally. As December progresses and Three-Eye Atlas reaches its closest approach, then begins receding, as observations accumulate and papers publish, as amateur and professional astronomers document this visitor. We're writing a chapter in the long story of human understanding. Not the final chapter, not even necessarily an especially pivotal one, but our chapter, our contribution to the endless project of comprehension. Future observers will add their chapters. The story continues beyond us, beyond our lifetimes, beyond our civilization potentially.
But we're part of it, links in the chain connecting ancient Babylonian astronomers to whatever far future beings might one day look back at Earth's astronomical record and recognize our efforts to understand. That continuity matters. It situates us in something larger than ourselves, larger than our era, larger than humanity itself. The project of understanding the cosmos transcends any individual or group. It's a multi-generational, multi-millennial effort that may have no endpoint, just deeper and deeper comprehension approaching, but never quite reaching complete knowledge. And that's beautiful. The universe doesn't surrender its secrets easily. It makes us work for understanding. But in that work, in the patient observation and careful analysis and honest acknowledgement of uncertainty, we fulfill something fundamental about being conscious, intelligent, curious. We are the universe becoming aware of itself. A poetic phrase, but accurate. The atoms that make our bodies and brains were forged in stellar cores. Those atoms, through evolution and development, organized into structures capable of observing and pondering the cosmos from which they came. In us, the universe observes itself. In our science, the universe develops understanding of its own processes. Three Eyes Atlas, drifting through its billion-year journey, doesn't know it's being observed, doesn't know that a brief blue planet third from an average star happened to have evolved intelligent life during the cosmic moment of its passage, doesn't care about the papers being written or the debates about its nature. But we know, we care, and through our knowing and caring, through our observations and analyses, we're creating meaning where only physics existed before. Not meaning imposed from outside, but meaning emergent from the interaction between conscious minds and cosmic phenomena. That's enough. That's sufficient. That justifies the cold pre-dawn observing sessions, the years of training to become competent astronomers, the societal resources allocated to telescopes and research programs. Because in understanding Three Eye Atlas, we understand ourselves better. We understand our place in space and time. We understand that we're part of something vast and ancient and ongoing. And so as this visitor continues its journey, accelerating away from the sun toward the outer solar system and eventually back to interstellar space, we watch as long as we can. We gather every photon, analyze every spectrum, track every position. We learn what we can while opportunity permits. Then we let go. We acknowledge that Three Eye Atlas will continue its journey beyond our reach, carrying whatever mysteries it retains into the vastness perhaps, to be observed by other intelligences around other stars billions of years hence. Or perhaps to drift forever, a cosmic wanderer seen only this once by a briefly technological species on a small planet in an ordinary galaxy. Either way, we were here. We observed, we wondered, we tried to understand. That's the human story in miniature. We encounter mysteries, we investigate, we learn what we can, we pass our knowledge to future generations. And the project continues, endless and endlessly fascinating, as long as curious minds persist to pursue it. Three Eye Atlas came from the stars and returns to them, but for this brief moment it passed through our sky, and we were watching. The final question lingers. As this ancient traveler recedes into darkness, having revealed some secrets, while guarding others, ask yourself, how many others have passed through unwatched, unnoticed, carrying stories from distant star systems we'll never hear? How many more will come bearing messages from regions of the galaxy we can barely imagine? And when the next interstellar visitor arrives, because there will be a next one, what will we have learned from Three Eye Atlas that helps us see more clearly, understand more deeply, ask better questions? The universe is patient. It's been revealing itself gradually for 4 billion years of life on Earth, consciously observed only for the last few millennia. It will continue revealing itself long after we're gone if we're not careful to persist. But for now, in this moment, we're here to witness, to wonder, to work toward understanding. Three Eye Atlas is one visitor among countless others across cosmic time.
But it's our visitor, our moment, our opportunity, and we're making the most of it, one observation at a time, building knowledge, photon by photon, advancing human understanding incrementally but inexorably toward deeper truths. The comet doesn't care. The universe doesn't care. But we care. And that caring, that curiosity, that drive to comprehend, that's what makes us human. That's what makes this moment matter. Look up. If you can observe, if you can't at least acknowledge that above you right now an interstellar wanderer is passing through, carrying information from the ancient galaxy, offering insights to those patient enough to look and humble enough to admit what they don't know. That's the gift Three Eye Atlas brings. Not certainty, but questions. Not answers, but opportunities. Not conclusions, but invitations to keep exploring, keep learning, keep wondering. Accept the invitation. The universe is vast, ancient, and strange,
But it's knowable bit by bit, observation by observation, generation by generation. And every moment we spend trying to know it better, we fulfill our deepest nature as conscious beings, privileged to witness the cosmos from the inside. Three-Eye Atlas will soon be gone, but the questions it raised will persist. The data it provided will remain, and the next interstellar visitor will arrive, bringing new mysteries, new opportunities, new invitations to wonder. Will you be watching,